Before a single human being had ever left the atmosphere, someone had already designed a city for them to live in when they got there. Not a capsule, not a laboratory module bolted to a pressurized cylinder. A city, with corridors wide enough to walk without grabbing handholds, with floors that stayed beneath your feet, with water that fell downward when you poured it, and furniture that did not drift when you let go of it, and sleep that came without strapping yourself to a wall. The year was 1952. The drawings were precise, the engineering was serious, and the man who made them had already helped design the rockets that would one day make it possible to build what he was imagining. We never built it. That fact, quiet, almost unremarkable after 7 decades, is one of the most consequential decisions in the history of human spaceflight. Not because the design was perfect, not because it would have solved every problem we later encountered beyond Earth, but because the problem it was designed to solve has never gone away, and the longer we wait, the more clearly we can see exactly what that delay has cost us. The man was Wernher von Braun. The design was a rotating space station, a great wheel, turning slowly in orbit, generating through its spin what the vacuum of space refused to provide. Gravity, not the faint suggestion of it, not a partial fraction. Gravity. Steady, reliable, measured, manufactured. And before you set that aside as retro science fiction, the kind of thing that belongs alongside flying cars and dome cities on Venus, understand what it actually was. It was not a dream sketched on a napkin by someone with too much imagination and too little engineering experience. It was a program proposal, a roadmap, a sequence of steps laid out in precise order, published in a major American magazine, read by millions, illustrated with technical diagrams that aerospace engineers reviewed and did not dismiss. The sequence began with heavy lift rockets. Then came the rotating station, built in orbit from components launched in pieces and assembled by crews working in the void. Then, using that station as a staging point, missions to the Moon, then Mars. In that plan, the Moon landing was not the beginning, it was step 3. Step 2 was the wheel. And we skipped it. To understand why that matters, why it still matters, here in the 3rd decade of the 21st century, when we are once again talking seriously about returning to the Moon and eventually sending people to Mars, you have to understand what the wheel actually was. Not the romantic version, not the iconic artwork of a spoked ring floating against a field of stars, the engineering reality. The design that von Braun and his colleagues published called for a structure roughly 250 feet across, 75 meters in diameter, give or take. That is smaller than a football field. Smaller than many of the buildings you pass on an ordinary walk through a city, by the standards of the orbital megastructures that theorists would propose in later decades. The mile-wide Stanford Torus, the 20-mile O'Neill cylinder, it was almost modest. A frontier outpost, not a metropolis. It consisted of a central hub, connected by spokes to an outer rotating ring. The hub stayed still, serving as a docking port for arriving spacecraft. The ring turned, and as it turned, anything standing on the inner surface of that ring was pressed outward by centrifugal acceleration, the same force that pins you to the wall of a spinning carnival ride, the same principle that pulls water to the edge of a washing machine drum during the spin cycle. At the right rotation rate, that outward acceleration would feel, to anyone standing in the ring, indistinguishable from the pull of a planet beneath their feet. The station was designed to house roughly 1,000 people, scientists, engineers, technicians, military observers, because Cold War realities were never far from 1950s planning. They would live in the rotating ring in conditions that, while Spartan, would not require them to spend hours each day exercising simply to prevent their bones from dissolving or their hearts from weakening. They would, in other words, live like humans rather than endure like astronauts. If you are not familiar with what prolonged weightlessness does to the human body, the details are worth pausing on, not because they are dramatic, they are in fact relentlessly mundane, which is precisely what makes them so sobering. In the absence of gravity, the skeleton begins to lose density, not immediately, not catastrophically. Gradually, at a rate of roughly 1 to 2% per month, in the most affected regions, the hips, the spine, the legs. Muscle mass follows. The cardiovascular system, no longer required to pump blood upward against gravity, restructures itself. The fluid that normally pools in your lower body redistributes toward your head, producing a persistent facial puffiness that astronauts describe as feeling permanently congested. Vision can change, sometimes permanently, as cerebrospinal fluid shifts and presses against the optic nerve. None of this was known in 1952. The medical data would come later, through Mercury and Gemini and the long-duration missions aboard Skylab and Mir, and eventually the International Space Station. But von Braun's team did not need medical studies to recognize a simpler truth. Humans evolved in gravity. Remove it, and problems would follow. The body does not know it is in space. It knows only that the conditions it was built for no longer exist, and it begins, quietly and efficiently, to dismantle the systems it no longer needs. Artificial gravity was not, in their thinking, a luxury. It was baseline infrastructure, the same category of necessity as air, water, and thermal regulation. You do not justify including oxygen in a spacecraft. You do not explain why you would prefer your crew to remain warm. And in the world that von Braun imagined, a world where humans would live in space for years, not weeks, you did not need to justify providing them with gravity either. But here is what most people get wrong when they encounter this history. They assume the wheel was abandoned because it was impractical, too complex, too expensive, beyond the engineering capability of the era. A beautiful idea that ran headlong into the limits of what 1950s and 1960s technology could actually accomplish. That is not what happened. The technology was not the obstacle. The sequence was. When the space race accelerated in the late 1950s and early 1960s, driven not by scientific ambition but by geopolitical terror, by the shock of Sputnik, by the fear of Soviet dominance in a domain that seemed to offer military and psychological supremacy. Unlike anything in human history, the careful logic of von Braun's roadmap was overwritten by urgency. The goal was no longer to build space infrastructure methodically. The goal was to plant a flag on the moon before the Soviets did. And the fastest path to that flag did not run through a rotating station in low Earth orbit. It ran directly from a launch pad in Florida to the lunar surface. So we inverted the sequence. We went to the moon first. We built stations later, but we built them wrong, not wrong in the sense that they failed because they did not fail, because they taught us extraordinary things about physics and biology and human psychology under conditions no previous generation had ever faced. Wrong in a different sense. Wrong in the sense that we built them without the one feature that von Braun had considered non-negotiable. We built them without spin. Skylab did not rotate, Salyut did not rotate, Mir did not rotate. The International Space Station, a structure that took more than a decade to assemble, that represents one of the most complex engineering achievements in human history, that has been continuously inhabited for more than 2 decades, does not rotate. Not one of the stations we have ever actually constructed has provided its crew with artificial gravity, and we have been paying that price ever since. There is a number that surfaces occasionally in reporting about life aboard the International Space Station, a number that tends to slide past without quite registering the way it should. Astronauts aboard the ISS consume sleep medication at a rate approximately 10 times higher than the American general population. And the American general population's sleep medication usage is itself already considered by most public health researchers to be quite high. Think about what that means. The most carefully selected, most intensively trained, most medically screened human beings on the planet, people chosen in part for their psychological resilience and physiological robustness, require pharmaceutical assistance to sleep at a rate, an order of magnitude above that of ordinary people living ordinary lives. This is not a failure of individual astronauts. It is a failure of the environment, an environment we designed, an environment we have been refining for 60 years and have still not fixed at its most fundamental level. The station smells. Ask any astronaut who has served aboard it. They all have stories, and the stories are consistent. A closed system with hundreds of mechanical components, recycled air, 6 human bodies, and limited ventilation does not smell like anything you would choose to spend time in. It smells like what it is, a machine that humans are living inside of, rather than a place built for human habitation. Plants grow in arbitrary directions, spiraling toward light sources without the gravitational orientation that guides root and stem development on Earth. Fluids must be pumped rather than poured. Sleeping requires restraint systems. Showering is effectively impossible. Crews use rinseless shampoo and wet wipes. Toilets depend on airflow dynamics rather than the simple logic of water moving downward. Every routine task, every meal, every maintenance procedure, every moment of recreation requires adaptations that would be unnecessary in any gravity environment, no matter how modest. This is the world we chose, not because it was better, because it was faster. Now consider what was available to us instead. In 1965, the Saturn V was in development. The Atlas and Titan rockets were already flying. The engineering knowledge required to assemble structures in orbit was being acquired through the Gemini program, mission by mission. The materials science, the welding techniques, the pressurization systems, all of it existed or was being actively developed. A rotating station 75 meters across, launched in modular segments and assembled in low Earth orbit, was within the technical reach of that era. Not easy, not cheap, but within reach. The way the lunar landing was within reach, demanding, unprecedented, requiring sustained commitment and significant resources, but not requiring the discovery of new physics or the invention of materials that did not yet exist. We could have built it. We chose not to. And 70 years later, the question that hangs over every serious conversation about human expansion into space is still the same one. Von Braun was trying to answer with his spinning wheel in 1952. How do you keep a human being alive and healthy and functional, not for a mission but for a life? If you find yourself drawn to questions like this one, questions that start with engineering and end somewhere closer to philosophy, then this is the kind of journey we take on this channel. And if you enjoy it, doing me the small favor of hitting that like button and subscribing genuinely helps this channel reach more people who are asking the same questions. We are going to follow this thread all the way through, from the physics of a spinning ring to the moment when a crew steps off a rotating ship onto the surface of Mars, without their legs giving out beneath them. From a blueprint drawn before the space age began, to the network of turning wheels that may one day form the circulatory system of an interplanetary civilization. Find yourself somewhere comfortable. Let's begin. The first thing to understand about artificial gravity is that it is not, in any meaningful sense, artificial. Gravity, in the Newtonian framework that governs our everyday experience of physics, is acceleration. When you stand on the surface of the Earth, you feel a force pressing you into the ground because the ground is pushing back against the Earth's gravitational pull. Remove the ground, step off a cliff, or fall freely in any direction, and you become weightless. Not because gravity has disappeared, because nothing is pushing back. This is the condition that astronauts experience in orbit. They are not beyond Earth's gravity. At 400 kilometers above the surface, Earth's gravitational pull is still roughly 90% of what you feel standing on the ground right now. What they have done is fall sideways fast enough that the ground keeps curving away beneath them. They are in continuous freefall. The sensation is weightlessness, but the reality is a very precise application of gravitational force in a very specific direction. Now consider what happens when you spin something. Imagine you are holding a ball on a string, and you swing it in a circle above your head. The ball wants to travel in a straight line. That is what objects do when no force acts on them. The string pulls it inward, bending its path into a circle. From the ball's perspective, if a ball could have a perspective, there is a force pulling it outward, away from the center of rotation. That outward pull is what we call centrifugal force. And while physicists will note that it is technically a fictitious force, an artifact of being in a rotating reference frame rather than a real push, it is entirely real in its effects. It is what presses you into the seat of a car going around a corner. It is what pins a motorcyclist to their seat in a loop. It is what makes the water stay in a bucket when you swing it fast enough overhead. And it is exactly what would press the feet of a crew member in a rotating space station firmly to the floor of the outer ring. The mathematics of this are straightforward enough to state without equations. The centrifugal acceleration at any point on a rotating ring depends on two things: the radius of the ring, how far you are from the center of rotation, and the rotation rate, measured in revolutions per minute. Increase the radius, and for the same rotation rate, the acceleration increases. Increase the rotation rate, and for the same radius, the acceleration increases faster still. It scales with the square of the rotation rate, meaning that doubling the spin quadruples the felt gravity. For the von Braun wheel, with a radius of roughly 37 meters, generating something close to Earth's surface gravity at the rim would require a rotation rate of approximately 5 revolutions per minute. That is one full rotation every 12 seconds. Fast enough to be perceptible if you watch the stars through a window. Fast enough to produce what engineers call Coriolis effects, subtle distortions in the apparent motion of objects caused by the fact that the reference frame itself is rotating. Pour a glass of water in a 5 RPM station and the stream will not fall perfectly straight. It will curve slightly, deflected by the rotation. Toss a ball across the room, and it will arc in a direction your instincts did not predict. Turn your head quickly from side to side, and your inner ear, a system evolved to interpret motion in a non-rotating environment, will send signals to your brain that do not quite match what your eyes are seeing. This is not debilitating. Humans are adaptable in ways that continue to surprise researchers. Studies of rotating environments and centrifuge exposure suggest that most people can habituate to Coriolis effects at 5 RPM within a matter of days, sometimes hours. The disorientation fades, the body recalibrates. What felt strange becomes unremarkable. But it is worth acknowledging, because it was one of the reasons that subsequent habitat designers pushed for larger structures. The Stanford torus, with a radius of nearly 900 meters, could achieve Earth gravity at less than 1 revolution per minute, slow enough that Coriolis effects would be essentially imperceptible, slow enough that a resident might live their entire life in the station without ever consciously registering that they were rotating at all. The von Braun wheel could not offer that. At 75 meters across, it was the smallest practical demonstration of the principle at settlement scale, not optimized, not comfortable in every way, but functional. A compromise between what physics demands and what the launch technology of the era could lift into orbit. It was the log cabin, not the manor house, and like all log cabins in the history of frontier settlement, its value was not in its elegance. Its value was in being first. There is a date that changed the sequence of everything. The 4th of October, 1957. A sphere the size of a beach ball, weighing 83 kilograms, rose above the Soviet steppe on a column of fire and entered orbit. It transmitted nothing more sophisticated than a radio beep, a steady pulse, repeating, unremarkable in content, devastating in implication. Sputnik, the world's first artificial satellite. And the moment it appeared on American radar screens, the careful, methodical roadmap that von Braun had spent years constructing began to come apart. Not because Sputnik proved that the roadmap was wrong. It proved the opposite, that the Soviets were moving fast, that space was not a distant philosophical frontier but an immediate strategic domain, and that whoever established dominance there first would hold an advantage that no previous era of human competition had offered. The roadmap was right. The problem was that following it correctly would take time that suddenly felt impossible to spend. The rotating station was step 2. Step 2 required step 1 to be complete. The development of heavy-lift rockets capable of carrying the modular components of a wheel-shaped structure into low Earth orbit in sufficient numbers to actually assemble it. And step 1, in 1957, was still years away. The moon was step 3, but the moon was visible. The moon was symbolic. The moon was, in the language of geopolitics, a flag that the entire world could see planted from hundreds of thousands of miles away. So the decision was made, not in a single meeting, not by a single person, but through the accumulated pressure of a decade of Cold War, anxiety, and congressional budget cycles and presidential ambition. We would go to the moon, directly, without the station. without the rotating foundation that von Braun had always insisted should come first. We inverted the sequence, and in doing so, we committed ourselves to a particular vision of what space would be, not a place to live, but a place to visit, not a domain to inhabit, but a frontier to touch and photograph and return from. To understand what that inversion cost, you have to follow the timeline forward. The 20th of July 1969, Neil Armstrong steps onto the lunar surface. The flag is planted, the photographs are taken, the rocks are collected, and then, in the months and years that follow, something unexpected happens, not to the mission, which succeeds beyond any reasonable expectation, but to the program that surrounds it. The urgency evaporates. Once the flag was on the moon, the geopolitical logic that had driven the entire enterprise began to lose its grip on the institutions that funded it. Apollo continued 5 more successful landings, one nearly catastrophic mission that became its own kind of triumph, but the momentum was already bleeding away. By the time Apollo 17 left the lunar surface in December 1972, the program was over. No follow-on lunar base, no permanent presence. The most extraordinary journey in human history, and we went 6 times and stopped. What came next was Skylab, America's first space station, launched in 1973, a repurposed Saturn V upper stage converted into a habitable volume. It was, in many ways, a remarkable achievement larger than anything previously flown, capable of hosting crews for months at a time, yielding genuine scientific data about long-duration spaceflight that no previous mission had produced. But it did not rotate. There had been discussions. There were always discussions. The concept of adding a rotating section to Skylab, or of designing its successor with artificial gravity, surfaced repeatedly in the engineering conversations of that era. Each time, the conclusion was the same. It would add complexity. It would add cost. It was not strictly necessary for the missions being planned, which were already time-limited, already designed around the assumption that crews would return to Earth before the effects of weightlessness became truly damaging. Not strictly necessary. That phrase, quiet, reasonable, fiscally defensible, is how civilizations make the decisions they later spend decades regretting. The Soviets, for their part, pursued a different path, though not toward rotation either. The Salyut program, beginning in 1971, and its successor Mir, which flew continuously from 1986 to 2001, established the architecture of long-duration spaceflight that the world still largely uses today. Cylindrical modules, docking ports, modular expansion, no spin. What Mir gave us, beyond the political symbolism of continuous Soviet and then Russian presence in space, was data. Brutal, honest, physiologically unambiguous data about what happens to human beings when they spend not weeks, but months, and eventually more than a year in microgravity. The results were not encouraging. Cosmonaut Valery Polyakov spent 437 days aboard Mir between 1994 and 1995, a record for continuous spaceflight that still stands. When he returned to Earth, he was able to walk from the landing capsule with assistance, a symbolic gesture that his medical team had rehearsed carefully, because the alternative optics were considered unacceptable, but the recovery process took months. His bones had shed density at a rate that, sustained indefinitely, would have led to structural failure. His muscles had atrophied. His cardiovascular system had restructured itself around the assumption that it would never again need to pump blood against the pull of a significant gravity field. 437 days. That is roughly the transit time for a one-way journey to Mars under favorable orbital conditions. Sit with that for a moment. The longest continuous spaceflight in human history lasted approximately as long as it would take to reach our nearest planetary neighbor, and the person who completed it required months of rehabilitation before he could be considered physiologically recovered. If we sent a crew to Mars tomorrow in a spacecraft with no rotating section, no artificial gravity, nothing but the microgravity environment that every crewed spacecraft in history has provided, they would arrive at their destination in roughly the same condition as Polyakov when he stepped off Mir. Except they would not have a recovery team waiting for them. They would not have a rehabilitation facility. They would not have the option of lying quietly in a bed while their bones remembered how to bear weight. They would have a planet to land on, a mission to execute, work that could not wait. The International Space Station arrived at the end of the 20th century as the most complex collaborative engineering project in human history. 16 nations, more than a decade of assembly, 420 metric tons of metal and polymer and electronics, orbiting 400 kilometers above your head right now, a structure so large it is visible to the naked eye on a clear night, moving across the sky like a bright and purposeful star. It is a genuine marvel. There is no honest way to describe it that does not acknowledge the scale of what it represents, the sustained cooperation, the technical achievement, the accumulated scientific knowledge it has generated across more than 2 decades of continuous human habitation. And it does not rotate. There were proposals. There have always been proposals. In the 1980s and early 1990s, as the station was being designed, the possibility of including a rotating habitation module was raised and seriously studied. The engineering was not the obstacle. The mass budget was. The cost was. The complexity of integrating a rotating system with the station's existing architecture, the need for mechanical or magnetic bearings capable of maintaining separation between rotating and non-rotating sections over years of operation, the challenge of managing the gyroscopic effects that a spinning mass would introduce into the station's attitude control. All of these were real engineering problems, solvable but expensive, and again, not strictly necessary. The missions were months long. People would exercise, people would return. The station was a laboratory, and laboratories do not need to be comfortable. They need to generate data. So the engineers who might have designed the bearing system went to work on other problems. The budget that might have funded a rotating module went to other line items. And the International Space Station was built exactly as it was designed, brilliant, unprecedented, and fundamentally unsuited to the kind of long-duration human habitation that every serious plan for deep space exploration requires. Here is a number that does not appear in most news coverage of the space station, but should. The recommended daily exercise regimen for astronauts aboard the ISS is 2.5 hours, every day, 7 days a week. Not because the astronauts enjoy it, not because NASA has developed a particularly progressive attitude toward workplace wellness, because without it, the rate of bone density loss and muscle atrophy accelerates to a point that makes reintegration into Earth's gravity environment genuinely dangerous. 2.5 hours per day. That is time that is not spent on science, not spent on maintenance, not spent on the psychological recovery that comes from having a few hours each day with no obligation. It is time spent fighting the environment, time extracted from every other activity that the crew might otherwise perform, in service of the single project of keeping bodies functional that were not designed for the conditions they are living in. On a 6-month mission, that adds up to more than 450 hours of mandatory exercise, more than 11 full 40-hour working weeks, consumed entirely by the task of mitigating the effects of weightlessness. Now imagine that same mission conducted aboard a rotating station, where the crew steps off their shift and walks, not floats, not carefully navigates with handholds to a dining area, sits down at a table, eats a meal from a plate that stays where it is placed, and then sleeps in a bed without strapping themselves to the wall. The exercise requirement does not disappear. Cardiovascular health demands physical activity regardless of gravity environment. But the mandatory remediation, the hours spent simply preventing the body from deteriorating, shrinks dramatically. Bones bear weight. Muscles resist gravity. The cardiovascular system maintains the architecture it evolved for. The crew arrives at the end of a long mission not as patients requiring rehabilitation, but as people who have been living in a demanding but inhabitable environment. That is the difference between a laboratory and a home. And it is a difference measured not in philosophy, but in hours. Hundreds of hours, per crew member, per mission. The accumulation of this data, 60 years of it now, gathered across Mercury and Gemini and Apollo and Skylab and Mir and the ISS and every long-duration mission in between, has produced a conclusion that the aerospace medical community has been approaching for decades without quite stating in its bluntest form. Human beings cannot live indefinitely in microgravity without paying a price that eventually becomes incompatible with the missions we are asking them to perform. That is not a controversial finding. It is not disputed by any serious researcher in the field. The only question is how long the incompatibility can be managed through countermeasures, exercise, pharmacology, nutrition, carefully engineered fluid dynamics, before the countermeasures themselves become the limiting factor on mission duration and crew capability. For short missions, the answer is long enough. For missions to the moon, measured in days, microgravity is an inconvenience rather than a crisis. For missions to the ISS, measured in months, it requires significant mitigation but remains manageable. For missions to Mars, measured in years, the transit, the surface operations, the return, the honest answer is we do not know. And that uncertainty is not the kind that resolves itself through optimism. What makes this history genuinely strange, what gives it the quality of a choice that seemed reasonable in the moment and only reveals its full cost in retrospect, is that the alternative was always visible. Von Braun's drawings were never classified. The physics of rotating habitats were never disputed. The engineering challenges were never declared insurmountable. At every point in the past 70 years, someone in a position to make the decision could have said, "We need to build a rotating station. We need to solve the gravity problem before we commit to missions that the absence of gravity will compromise." That decision was never made. Not because the argument was wrong, because the argument was never urgent enough to displace whatever other priority occupied the budget and the attention of the relevant institutions at the relevant moment. In the 1960s, the priority was reaching the moon before the Soviets. In the 1970s, the priority was demonstrating that humans could live in space at all. In the 1980s, the priority was building a station that 16 nations could agree on and fund. In the 1990s and 2000s, the priority was completing the International Space Station. And always, underneath every conversation, the same quiet phrase, "Not strictly necessary. Not yet. We will get to it." We have been getting to it for 70 years. There is a specific kind of loss that comes from a road not taken, not the dramatic loss of catastrophe, not the visible loss of failure, but the invisible loss of a world that could have existed and does not. We cannot point to the crew members who suffered health consequences that a rotating station would have prevented, because we cannot know who they would have been, or what those consequences would have looked like in a different history. We cannot quantify the science that was not done because researchers were spending 2.5 hours a day exercising instead. We cannot measure the missions that were not attempted because the physiological risks of long-duration microgravity made them too dangerous to sanction. What we can do is look at where we are today. We can note that every serious proposal for a crewed Mars mission includes, somewhere in its risk analysis, a section on the physiological effects of the interplanetary transit. We can observe that the proposed mitigation strategies, more exercise, better pharmacology, carefully designed counter-pressure suits are all variations on the same approach we have been refining for 60 years, with the same fundamental limitation. They address the symptoms of weightlessness without addressing its cause. The cause is the absence of gravity. The solution is gravity. And the machine for manufacturing gravity in space is a rotating structure, the same rotating structure that appeared in von Braun's engineering drawings in 1952, that has appeared in every serious proposal for long-duration human spaceflight since, and that we have never actually built. Not because we could not, because we kept deciding it was not quite urgent enough, yet. But urgency has a way of arriving without announcement. The timeline for returning humans to the moon is now measured in years, not decades. The conversation about crewed Mars missions has moved from theoretical to programmatic. Private companies are designing orbital habitats. Space agencies are collaborating on lunar gateway stations. The next chapter of human spaceflight is no longer a distant aspiration, it is an active engineering project, with contracts and timelines and budget lines. And running through all of it, like a thread that has never been cut, but has also never been followed to its end, is the question that von Braun was trying to answer with his spinning wheel. How do you keep a human being not just alive, but genuinely functional? not for a mission, but for a life in the environment beyond Earth? The answer, the same answer it has always been, begins with rotation. And the next question, the question that the rest of this journey will work through, piece by piece, is not whether we should build rotating habitats. That debate has been settled by 60 years of physiological data and the accumulated weight of every long-duration mission ever flown. The question is what those habitats look like, how we build them, what they become, and what kind of civilization grows up inside their spinning rings. That question starts not in orbit, but right here, with a sober look at whether the technology we have today is finally sufficient to do what the technology of 1965 might have managed if anyone had been willing to commit to it. Let us start with mass, not as an abstraction, as a specific number, the kind of number that engineers write on whiteboards and argue about in conference rooms and ultimately use to decide whether something gets built or stays on paper. The International Space Station, as it exists today, masses approximately 420 metric tons. That is 420,000 kilograms of metal, polymer, electronics, insulation, plumbing, wiring, scientific equipment, and habitable volume, assembled over more than a decade of construction flights, piece by piece, module by module, in one of the most logistically complex undertakings in the history of engineering. 420 metric tons. Remember that number. Now, consider what a von Braun-style rotating station would actually require in terms of mass. Not the romantic version, not a gleaming white wheel with 1,000 personnel living in comfort, the version that appeared in the Collier's illustrations that shaped a generation's imagination, the practical version, a rotating ring 75 to 100 meters in diameter, built with modern materials, optimized structural geometry, and modular assembly techniques. Habitation for a crew of perhaps 50 to 200, depending on the configuration. Radiation shielding, life support, power generation, docking capability at the central hub. The honest engineering estimate, accounting for structural reinforcement, adequate for a rotating system and radiation shielding sufficient for long-duration occupancy, places such a station somewhere in the same order of magnitude as the ISS. Perhaps somewhat heavier, if full Earth gravity is the target at the rim. Perhaps considerably lighter, if the design aims for Martian gravity 38% of Earth's surface value, which would require a slower rotation rate and therefore less structural stress on the ring. Even if you double the ISS mass to account for the additional complexity of a rotating system, even if you assume that every engineering uncertainty resolves against you, that every component comes in heavier than the baseline estimate, that redundancy requirements add mass at every level, you are still describing something that could, in principle, be launched to orbit in pieces over the course of a few dozen heavy lift flights. A few dozen flights. That is not a civilization-scale mobilization. That is a logistics problem. To appreciate why that distinction matters, you have to understand what launch costs have done over the past decade. Not in the abstract, optimistic sense that space enthusiasts invoke when they want to suggest that everything is about to become easy, but in the specific, documented, auditable sense eye to eye. In the era of the space shuttle, that cost was approximately $54,000 per kilogram, not because the shuttle was poorly designed or the program was mismanaged in any simple sense, but because a partially reusable vehicle that required essentially complete refurbishment between flights that required thousands of personnel working for months to prepare each launch could not escape the fundamental economics of its own architecture. The Falcon 9, operating with a reusable first stage, brought that number down to somewhere between $2,000 and $3,000 per kilogram to low Earth orbit, a reduction of roughly 95%, an improvement so large that it belongs in a different category of analysis entirely. And the vehicles currently in development or early operation in the class of fully reusable heavy lift systems capable of carrying 100 metric tons or more to orbit per flight are targeting costs that may eventually approach a few $100s per kilogram, potentially lower as flight rates increase and the economics of reusability fully mature. What this means, in concrete terms, is the following. The launch problem for a rotating space station is not solved. Launch costs are not yet low enough to make orbital construction trivially affordable. But the launch problem has changed category. It has moved from existential to logistical, from a question of whether the technology exists to a question of how many flights, on what schedule, at what total program cost. That is a different conversation, and it is a conversation that becomes more favorable with every additional flight of a reusable heavy-lift vehicle. The mass is one part of the engineering picture. The assembly is another. We already know how to. Let us start with mass, not as an abstraction, as a specific number, the kind of number that engineers write on whiteboards and argue about in conference rooms, and ultimately use to decide whether something gets built or stays on paper. The International Space Station, as it exists today, masses approximately 420 metric tons. That is 420,000 kilograms of metal, polymer, electronics, insulation, plumbing, wiring, scientific equipment, and habitable volume assembled over more than a decade of construction flights, piece by piece, module by module, in one of the most logistically complex undertakings in the history of engineering. 420 metric tons. Remember that number. Now consider what a von Braun-style rotating station would actually require in terms of mass. Not the romantic version, not a gleaming white wheel with 1,000 personnel living in comfort, the version that appeared in the Collier's illustrations that shaped a generation's imagination. The practical version, a rotating ring 75 to 100 meters in diameter, built with modern materials, optimized structural geometry, and modular assembly techniques. Habitation for a crew of perhaps 50 to 200, depending on the configuration. Radiation shielding, life support, power generation, docking capability at the central hub. The honest engineering estimate, accounting for structural reinforcement, adequate for a rotating system, and radiation shielding sufficient for long-duration occupancy, places such a station somewhere in the same order of magnitude as the ISS, perhaps somewhat heavier if full Earth gravity is the target at the rim, perhaps considerably lighter if the design aims for Martian gravity 38% of Earth's surface value, which would require a slower rotation rate and therefore less structural stress on the ring. Even if you double the ISS mass to account for the additional complexity of a rotating system, even if you assume that every engineering uncertainty resolves against you, that every component comes in heavier than the baseline estimate, that redundancy requirements add mass at every level, you are still describing something that could, in principle, be launched to orbit in pieces over the course of a few dozen heavy-lift flights. A few dozen flights. That is not a civilization-scale mobilization. That is a logistics problem. To appreciate why that distinction matters, you have to understand what launch costs have done over the past decade. Not in the abstract, optimistic sense that space enthusiasts invoke when they want to suggest that everything is about to become easy, but in the specific, documented, auditable sense of what it actually costs to place a kilogram of payload in low Earth orbit. In the era of the space shuttle, that cost was approximately $54,000 per kilogram. Not because the shuttle was poorly designed or the program was mismanaged in any simple sense, but because a partially reusable vehicle that required essentially complete refurbishment between flights that required thousands of personnel working for months to prepare each launch could not escape the fundamental economics of its own architecture. The Falcon 9, operating with a reusable first stage, brought that number down to somewhere between $2,000 and $3,000 per kilogram to low Earth orbit, a reduction of roughly 95%, an improvement so large that it belongs in a different category of analysis entirely. And the vehicles currently in development or early operation in the class of fully reusable heavy-lift systems capable of carrying 100 metric tons or more to orbit per flight are targeting costs that may eventually approach a few $100s per kilogram, potentially lower as flight rates increase and the economics of reusability fully mature. What this means, in concrete terms, is the following. The launch problem for a rotating space station is not solved. Launch costs are not yet low enough to make orbital construction trivially affordable, but the launch problem has changed category. It has moved from existential to logistical, from a question of whether the technology exists to a question of how many flights, On what schedule? At what total program cost? That is a different conversation. And it is a conversation that becomes more favorable with every additional flight of a reusable heavy lift vehicle. The mass is one part of the engineering picture. The assembly is another. We already know how to build large structures in orbit. The International Space Station demonstrated this across more than 40 assembly flights conducted over 13 years. Crews working in extravehicular conditions in spacesuits, tethered to structures, operating in the thermal extremes of orbital day and night connected modules, deployed trusses, installed solar arrays, routed power and data cables, and gradually assembled a structure with an interior habitable volume comparable to a 6-bedroom house from components that arrived separately and had to be joined with a precision that left no margin for error. This was extraordinarily difficult. It was also successful, and it established a body of knowledge about orbital construction techniques. Let us start with mass, not as an abstraction, as a specific number, the kind of number that engineers write on whiteboards and argue about in conference rooms and ultimately use to decide whether something gets built or stays on paper. The International Space Station, as it exists today, masses approximately 420 metric tons. That is 420,000 kilograms of metal, polymer, electronics, insulation, plumbing, wiring, scientific equipment, and habitable volume assembled over more than a decade of construction flights, piece by piece, module by module, in one of the most logistically complex undertakings in the history of engineering. 420 metric tons. Remember that number. Now consider what a von Braun-style rotating station would actually require in terms of mass. Not the romantic version, not a gleaming white wheel with 1,000 personnel living in comfort. The version that appeared in the Collier's illustrations that shaped a generation's imagination. The practical version, a rotating ring 75 to 100 meters in diameter, built with modern materials, optimized structural geometry, and modular assembly techniques. Habitation for a crew of perhaps 50 to 200, depending on the configuration. Radiation shielding, life support, power generation, docking capability at the central hub. The honest engineering estimate, accounting for structural reinforcement, adequate for a rotating system, and radiation shielding sufficient for long-duration occupancy, places such a station somewhere in the same order of magnitude as the ISS. Perhaps somewhat heavier, if full Earth gravity is the target at the rim. Perhaps considerably lighter, if the design aims for Martian gravity 38% of Earth's surface value, which would require a slower rotation rate and therefore less structural stress on the ring. Even if you double the ISS mass to account for the additional complexity of a rotating system, even if you assume that every engineering uncertainty resolves against you, that every component comes in heavier than the baseline estimate, that redundancy requirements add mass, at every level you are still describing something that could, in principle, be launched to orbit in pieces over the course of a few dozen heavy lift flights. A few dozen flights. That is not a civilization-scale mobilization. That is a logistics problem. To appreciate why that distinction matters, you have to understand what launch costs have done over the past decade. Not in the abstract, optimistic sense that space enthusiasts invoke when they want to suggest that everything is about to become easy, but in the specific, documented, auditable sense of what it actually costs to place a kilogram of payload in low Earth orbit. In the era of the space shuttle, that cost was approximately $54,000 per kilogram. Not because the shuttle was poorly designed or the program was mismanaged in any simple sense, but because a partially reusable vehicle that required essentially complete refurbishment between flights that required thousands of personnel working for months to prepare each launch could not escape the fundamental economics of its own architecture. The Falcon 9, operating with a reusable first stage, brought that number down to somewhere between $2,000 and $3,000 per kilogram to low Earth orbit, a reduction of roughly 95%, an improvement so large that it belongs in a different category of analysis entirely. And the vehicles currently in development or early operation in the class of fully reusable heavy lift systems capable of carrying 100 metric tons or more to orbit per flight, are targeting costs that may eventually approach a few $100s per kilogram, potentially lower as flight rates increase and the economics of reusability fully mature. What this means, in concrete terms, is the following. The launch problem for a rotating space station is not solved. Launch costs are not yet low enough to make orbital construction trivially affordable, but the launch problem has changed category. It has moved from existential to logistical, from a question of whether the technology exists to a question of how many flights, on what schedule, at what total program cost. That is a different conversation, and it is a conversation that becomes more favorable with every additional flight of a reusable heavy-lift vehicle. The mass is one part of the engineering picture, the assembly is another. We already know how to build large structures in orbit. The International Space Station demonstrated this across more than 40 assembly flights conducted over 13 years. Crews working in extravehicular conditions in spacesuits, tethered to structures, operating in the thermal extremes of orbital day and night connected modules, deployed trusses, installed solar arrays, routed power and data cables, and gradually assembled a structure with an interior habitable volume comparable to a 6-bedroom house from components that arrived separately and had to be joined with a precision that left no margin for error. This was extraordinarily difficult. It was also successful, and it established a body of knowledge about orbital construction techniques, crew coordination in vacuum environments, and the management of large-scale assembly sequences in microgravity that did not exist before the ISS program began. What we have not done is assemble a rotating structure in orbit. That is a meaningful distinction, and it deserves honest treatment rather than casual dismissal. A rotating station introduces assembly challenges that a static structure does not face. The ring segments must be joined with sufficient precision that the completed structure is dynamically balanced, that its mass is distributed symmetrically enough around the axis of rotation that spinning it up does not introduce vibrations that propagate through the structure and compromise both the hardware and the crew. An unbalanced rotating structure does not simply wobble in an inconvenient way. It wobbles in a way that is self-reinforcing, that transfers energy into the structure at the resonant frequencies of its components, and that can, if uncorrected, lead to mechanical failure. This is a solvable problem. It is solved routinely in rotating machinery on Earth, in turbines, in centrifuges, in the electric motors, in every appliance in your home. The technique is called dynamic balancing, and it involves measuring the imbalances in a rotating system and adding or removing small masses at specific locations to bring the system into equilibrium. Applied to an orbital station, it would require careful mass accounting during assembly and the ability to make fine adjustments once the structure begins to spin. Difficult, not mysterious. The bearing problem deserves similar treatment because it is the engineering challenge that comes up most often in conversations about rotating habitats, usually invoked as though it represents some fundamental obstacle that renders the entire concept impractical. The bearing problem is this: a rotating station must have at its center a hub that does not rotate or rotates at a different rate, so that spacecraft can dock with it without having to match the station's spin. Connecting a rotating ring to a non-rotating hub requires a mechanical interface that can transmit power, fluids, and data across the boundary between the two systems while allowing continuous relative rotation between them. This sounds exotic. It is not. The device that accomplishes this is called a rotary union, or in more complex implementations, a slip ring. Slip rings transmit electrical power and signals across a rotating interface. Rotary unions transmit fluids. Both technologies exist, are mature, are used in thousands of industrial applications on Earth, ranging from wind turbines to medical imaging equipment to radar antennas, and have been operating reliably in demanding environments for decades. The specific challenge for a space station is scale and longevity. The interface must function for years without maintenance access, in a vacuum environment, across a temperature range that cycles from roughly minus 150 degrees Celsius in shadow to plus 120 degrees in sunlight, with every orbital period of approximately 90 minutes. These are demanding conditions. They are also conditions that materials, scientists, and mechanical engineers understand well enough to design for. The ISS itself uses rotary joints called solar alpha rotary joints to allow its solar arrays to track the sun continuously while the main structure remains fixed in attitude. Those joints have been operating in orbit for more than 2 decades. The bearing problem, in other words, is an engineering problem. It has known solutions. Those solutions require careful design, quality materials, and rigorous testing. They do not require the discovery of new physics or the development of technologies that do not yet exist. There is one more technical challenge worth examining carefully, because it is the one that most directly affects the crew living inside the station rather than the engineers assembling it from the outside. This is the Coriolis effect, which appeared briefly in the first part of this journey and deserves a fuller treatment here. When you move inside a rotating reference frame, when you walk along the rim of a rotating station, or bend down to pick something up, or pour a liquid from one container to another, the fact that your reference frame is rotating means that your motion is not quite what a non-rotating observer would predict. Forces appear that have no counterpart in a non-rotating environment. A ball thrown across the room curves in a direction that your instincts, calibrated by a lifetime in a non-rotating world, did not anticipate. Fluid poured from a height lands slightly to one side of where you aimed. The magnitude of these effects depends on the rotation rate. At 1 revolution per minute, the rate achievable in a large structure, like the Stanford Torus, the Coriolis accelerations, are small enough that most people would never consciously notice them. At 5 revolutions per minute, approximately the rate required to generate Earth gravity in a 75-meter station, they are perceptible. Head movements can cause brief sensations of disorientation. Tasks requiring fine motor precision take slightly longer to master. The critical question is whether these effects are merely inconvenient or genuinely debilitating. And here the research, while incomplete, is reasonably encouraging. Studies conducted in rotating environments, in centrifuges, in slowly rotating rooms, in experiments designed specifically to assess human adaptation to Coriolis, conditions consistently find that most people adapt within days to rotation rates of up to 6 revolutions per minute. The adaptation is not merely psychological tolerance, it is a genuine recalibration of the vestibular system and motor control processes that allows the brain to update its predictions about how objects and limbs will move in the rotating environment. Some individuals adapt more slowly than others. Some experience nausea during the initial adaptation period, similar in character to motion sickness. A small percentage may never fully adapt to the higher rotation rates. These are real human factors considerations that would need to be addressed in crew selection and station design. But they do not represent a fundamental barrier. They represent design constraints, the kind of constraints that engineers work within, not around. A station that rotates at 3 to 4 revolutions per minute rather than 5, generating Martian rather than Earth gravity at the rim, would substantially reduce Coriolis effects, while still providing gravity sufficient to prevent most of the physiological deterioration associated with long-duration weightlessness. That may be the appropriate compromise for an early rotating habitat, not full Earth gravity, but enough gravity to matter, at a rotation rate low enough that adaptation is rapid and reliable. The perfect, in this as in so many engineering contexts, is the enemy of the good. A station that provides 60 or 70% of Earth's surface gravity is not ideal. It is vastly better than 0. And 0 is what every crewed station in history has provided. Step back from the individual technical challenges for a moment and look at the picture they form together. The mass required for a rotating station is comparable to what we have already demonstrated the ability to launch and assemble in orbit. The launch costs required to deliver that mass have fallen by more than 95% over the past 3 decades and continue to fall. The assembly techniques required to construct a rotating ring in orbit are extensions of techniques already validated during ISS construction. The bearing and rotary joint technologies required to connect a rotating ring to a non-rotating hub are mature, terrestrially proven, and have orbital precedent in the ISS solar array drive mechanisms. The Coriolis effects that concern crew habitability are manageable through design choices and human adaptation, particularly at moderate rotation rates. None of the obstacles are mysteries. None of them require fundamental breakthroughs. They require engineering, careful, thorough, well-funded engineering, the kind that produced the ISS and the Saturn V and every other major space infrastructure project in history. What they also require is a decision, a sustained, institutional decision of the kind that NASA made in 1961 when President Kennedy committed the United States to landing on the moon before the end of the decade. A decision that allocates resources and maintains them across administrations and budget cycles and competing priorities. A decision that treats the rotating station not as an optional enhancement to an existing program, but as foundational infrastructure for everything that comes after. That decision has not yet been made, but the conditions for making it are more favorable now than they have been at any previous point in the history of spaceflight. The launch economics are better. The construction knowledge is deeper. The physiological case for artificial gravity is stronger, built on 6 decades of medical data that did not exist when von Braun drew his wheel in 1952. And the missions that a rotating station would enable the missions that become possible or become safe only when crews can travel and live without the physiological burden of continuous weightlessness are no longer distant aspirations. They are items on active planning documents. There is a private company called VAST, founded in 2021, that is developing orbital habitat modules with long-term plans that include rotating structures. There is Gateway, the lunar orbital station being developed through NASA's Artemis program, which does not currently include rotation, but whose design evolution will be shaped in part by the physiological lessons of whatever long-duration missions precede it. There is Axiom Space, building commercial modules initially attached to the ISS, with ambitions that extend to freestanding stations. There are proposals from Sierra Space, from Blue Origin, from a dozen other organizations that have concluded, correctly, that the future of human presence in space is not government laboratories but inhabited infrastructure. None of these have yet committed to rotation. Most of them are at stages where the immediate priority is demonstrating that private orbital habitation is feasible at all, that modules can be built, launched, occupied, and maintained without the full institutional apparatus of a national space agency. That is the right priority for this moment. You do not design the city before you prove you can build a building. But the rotation question is present in every serious conversation about what comes after the first generation of commercial stations. The physiological data demands it. The mission profiles require it. The engineering is ready for it. What remains is will, and will in the history of spaceflight has always been the variable that determines everything else. Consider what the space around Earth could look like 50 years from now, if that will materializes. Not the optimistic version, the conservative version, the version that assumes normal rates of technological progress, normal levels of political and commercial investment, normal human ambivalence about large and expensive undertakings. In that conservative scenario, the first rotating habitat in orbit is probably something modest, a ring perhaps 50 to 100 meters across, providing partial gravity, Martian level perhaps, or slightly above, a crew of 20 to 50. A primary mission of long-duration physiological research, studying the effects of sustained partial gravity on human health across timescales of months and years. Secondary missions involving manufacturing, materials, science, and potentially agricultural experiments in a partial gravity environment. It is not glamorous. It is not the iconic wheel of the 1950s illustrations, with 1,000 personnel and a view of Earth through panoramic windows. It is a laboratory with a twist, literally. A research platform that happens to rotate. A machine for answering the questions that 60 years of microgravity research could not answer, because answering them required gravity that we never provided. But from that modest beginning, the logic of scaling is straightforward. A station that demonstrates safe, reliable operation of a rotating habitat over 2 or 3 years has answered the questions that currently block the path forward. It has shown that the bearing systems work over extended periods, that the dynamic balancing is maintainable, that crews adapt to the Coriolis environment without significant performance degradation. that the engineering of connecting rotating and non-rotating sections is manageable in practice, not just in simulation. Once those questions are answered, the next station is larger, and the one after that larger still. Not because there is a master plan requiring a specific progression, but because the technology and the knowledge and the investment followed demonstrated success. That is how every infrastructure system in human history has developed, not through a single grand act of vision, but through the accumulation of successful smaller steps, each one making the next step easier to justify and easier to fund. Von Braun understood this. His roadmap was not a blueprint for a single magnificent structure. It was a sequence, each step creating the conditions for the next. The rotating station was not the destination, it was the foundation. And foundations, by their nature, are invisible in the finished structure. Nobody photographs the concrete pilings beneath a skyscraper. Nobody writes poetry about the bearing systems inside a wind turbine. But without them, nothing above ground is possible. The wheel was always meant to be the foundation, not the monument, but the multiplier. Not the city, but the first street of the city, laid down in the darkness above the atmosphere, waiting for everything that would eventually follow. And now, finally, after 70 years of waiting, the tools to lay that street are in our hands. What we build with them, and when is the question that the rest of this journey will pursue. Because the rotating station is not just a habitat, it is a key, and the locks it opens lead somewhere that changes everything about how we think of our species and its future. The next door it opens leads to Mars. Mars is approximately 225 million kilometers from Earth at its closest approach. That number varies considerably. At its most distant, the two planets are separated by more than 400 million kilometers on opposite sides of the Sun, unreachable in any practical sense for years at a time. The favorable launch windows that allow a spacecraft to travel between the two worlds with reasonable fuel expenditure occur roughly every 26 months, when the orbital geometry aligns in a way that makes the journey possible without requiring propellant reserves that no current or near-future spacecraft could carry. Under the best available propulsion technology for a crewed mission, chemical rockets, the same fundamental technology that powered Apollo, refined and optimized, but not transformed, the transit from Earth to Mars takes somewhere between 6 and 9 months, depending on the specific trajectory chosen and the launch window used. 6 months at the aggressive end, using a fast transfer orbit that demands more fuel. 9 months on a more fuel-efficient path that follows the orbital mechanics more gently. Call it 7 months, a reasonable middle estimate. 7 months in a spacecraft. 7 months is approximately 210 days. In 210 days of microgravity, a human body loses somewhere between 5 and 10% of its bone mineral density in the most affected skeletal regions. Muscle mass in the legs and lower back, the muscle groups most dependent on gravity loading to maintain their volume, can decrease by 20% or more. The cardiovascular system restructures. The fluid distribution shifts. The visual system may be compromised by intracranial pressure changes that, in some astronauts, produce measurable alterations in the shape of the eyeball and lasting changes in visual acuity. And then the spacecraft arrives at Mars. Think carefully about what arrival means in this context. The crew does not dock at a comfortable station and spend 2 weeks in rehabilitation before beginning their work. There is no rehabilitation facility on Mars. There is no medical team waiting on a deck with steadying hands and careful eyes. There is a planet with a surface gravity of 3.7 meters per second, squared 38% of Earth's, and a mission that has been planned for years and cannot be postponed because the crew's legs are unreliable. They have to land in a vehicle whose descent and landing sequence will place physical demands on its occupants. They have to suit up, cycle through airlocks, and begin the surface operations that justify the entire enterprise. The geological surveys, the sample collection, the habitat setup, the scientific measurements that can only be taken by human beings who are present on the surface rather than observing through instruments from orbit. All of this performed by people whose musculoskeletal systems have spent 7 months in an environment that systematically dismantles the biological infrastructure required for exactly these activities. This is not a theoretical concern. It is not a worst-case scenario constructed for dramatic effect. It is the straightforward physiological consequence of the transit conditions that every current Mars mission architecture proposes, because every current Mars mission architecture assumes a non-rotating spacecraft. A spacecraft exactly like every crewed vehicle that has ever flown. The natural response is to suggest that the exercise countermeasures we have developed for the ISS will be sufficient. That if 2.5 hours per day of mandatory exercise can maintain crew health through 6-month ISS missions, similar protocols applied during a 7-month Mars transit will produce similar results. This argument has two problems. The first is that ISS countermeasures do not fully prevent physiological deterioration. They slow it. The bone density losses and muscle atrophy experienced by long-duration ISS crew members, despite rigorous exercise compliance, are real and measurable. The countermeasures are mitigation, not solution, and mitigation that is adequate for a mission that ends with return to Earth, and months of rehabilitation may not be adequate for a mission that ends with a planetary landing and immediate surface operations. The second problem is deeper. ISS crew members exercise for 2.5 hours per day in a vehicle that is, by orbital standards, spacious and well-equipped. The exercise hardware on the ISS, the Advanced Resistive Exercise Device, the treadmill, the cycle ergometer, was designed specifically for the station and is maintained by dedicated ground support teams. It occupies significant volume and mass. A Mars transfer vehicle is not the ISS. It is a spacecraft optimized for transit, not habitation. Every kilogram of exercise equipment is a kilogram not available for propellant, food, water, scientific instruments, or emergency supplies. Every hour of mandatory exercise is an hour not available for mission preparation, crew rest, or the psychological maintenance activities that keep human beings functional across 7 months of confinement in a metal cylinder. The countermeasure approach to microgravity on a Mars transit is not a solution. It is a very expensive, very demanding, and ultimately inadequate substitute for the thing that would actually solve the problem. The thing that would actually solve the problem is gravity. The simplest way to provide gravity on a spacecraft is the same way you provide it on a station. You rotate it. The geometry does not require a massive structure. 2 habitat modules connected by a long tether, spinning slowly around their common center of mass, generate centrifugal acceleration at each module proportional to the tether length and the rotation rate. Make the tether 200 meters long and rotate the system at 1 revolution per minute, and you generate approximately 1/10 of Earth's surface gravity. At each module, not enough to fully prevent physiological deterioration, but meaningful. Extend the tether to 400 meters, keep the same rotation rate, and you approach Martian gravity levels. This configuration, sometimes called a gravity gradient tether system, requires no rigid rotating ring, no complex bearing assembly, just a long, strong cable and 2 masses spinning slowly at its ends. It is not elegant. The tether introduces its own engineering. Challenges it must withstand the tension of the rotating system. It must be protected against micrometeorite impacts. It must be deployed and retracted reliably in the operational environment of deep space. But the engineering is tractable, and the physics is unambiguous. For a more robust solution, one that provides higher gravity levels, more habitable volume, and greater operational flexibility for a more robust solution, a rigid rotating section is the natural progression. A transfer vehicle built around a central spine, with cargo and propulsion at the hub, and habitation in a rotating ring at a radius of perhaps 50 to 75 meters, could provide Martian or near-Earth gravity throughout the cruise phase. During the engine burns required to depart Earth orbit and break into Mars orbit, the rotation could be slowed or stopped, then resumed once the burns are complete and the spacecraft is in the long, quiet arc of the transfer trajectory. This is not a concept developed for dramatic effect. It is a serious engineering approach that has been analyzed in detail by researchers at NASA and in the academic literature on human spaceflight. The mass penalty for including a rotating section in a Mars transfer vehicle is real. The structural complexity is real. The operational procedures for managing spin-up and spin-down around engine burns are real challenges that would require careful design and testing. But the mass and complexity of adequate exercise equipment, the physiological cost of insufficient countermeasures, and the mission risk of crews arriving at Mars in compromised physical condition are also real. And when those costs are placed honestly against each other, when the accounting is complete rather than selective, the rotating spacecraft begins to look not like an extravagance but like the more responsible choice. There is a concept in interplanetary mission design called the Aldrin cycler, named for Buzz Aldrin, the Apollo 11 astronaut who developed the orbital mechanics in the 1980s and has continued to advocate for the concept since. The cycler is an elegant solution to a specific problem. Getting from Earth to Mars and back again requires, under conventional mission architectures, that you carry all of your propellant with you, enough to depart Earth, enough to break into Mars orbit, enough to depart Mars, enough to break into Earth orbit. That propellant mass dominates the mass budget of any interplanetary vehicle and makes every mission enormously expensive. The cycler approach decouples the habitation problem from the propulsion problem. A cycler spacecraft is placed in a trajectory that takes it repeatedly between Earth and Mars, exploiting the gravitational dynamics of the two planets to maintain the orbit with minimal propellant expenditure. Once established, the cycler continues cycling indefinitely years, decades, in principle centuries, without requiring significant additional propulsion. It is, essentially, a perpetual interplanetary ferry that never stops moving. Crews do not travel from Earth to Mars in the cycler directly. They launch from Earth in a small, lightweight transfer vehicle, carrying only enough propellant for the short journey to intercept the cycler rendezvous with it during its Earth flyby, and ride it for the months of the transit to Mars. Near Mars, they transfer again to a Mars ascent and descent vehicle for the final leg of the journey. The process reverses for the return. The cycler itself, carrying no propellant for the main transit, can be as large and well-appointed as engineering allows. Its mass is not constrained by the fuel requirements of interplanetary propulsion. It can carry extensive radiation shielding, generous food and water reserves, medical facilities, exercise equipment, and most relevantly, a rotating habitation section. A cycler built around a rotating ring is not a compromise or a near-future speculation. It is the natural and logical design for a vehicle intended to carry human beings comfortably across interplanetary distances over a timescale of decades. The cycler's long operational life, its decades of continuous service, justifies the investment in more sophisticated habitation than a single mission vehicle could afford. The crew rides it for months. The rotating section provides gravity throughout. They arrive at Mars not as patients but as travelers. The cycler is civilization in motion, a piece of inhabited infrastructure that moves between worlds the way a ship moves between ports, not visiting the space between planets, but occupying it. But there is a deeper question beneath all of this, a question that the rotating station, the rotating spacecraft, and the Aldrin cycler all approach from different angles, but none of them fully answer alone. We know that zero gravity is incompatible with long-term human health. 60 years of data are unambiguous on this point. We do not know whether Martian gravity is sufficient. 38% of Earth's surface gravity, 3.7 meters per second squared. That is the gravitational environment that anyone living on Mars will inhabit, not for a transit, not for a mission, but potentially for years, potentially for a lifetime, potentially for generations. If Mars settlement becomes not an expedition but an emigration, no human being has ever lived in a sustained partial gravity environment. The data we have comes from two endpoints: Earth's surface gravity, which is what we evolved for, and the zero gravity of orbital spaceflight, which is what we have studied extensively. The vast territory between those endpoints, every gravity level from 1% to 99% of Earth normal, is essentially unexplored in terms of its long-term effects on human physiology. We do not know whether 38% gravity maintains bone density. We do not know whether it preserves cardiovascular architecture. We do not know whether children born and raised in Martian gravity would develop differently from children raised on Earth, whether their skeletal geometry would adapt to the lower loading, whether their muscle mass would distribute differently, whether returning to Earth would be physiologically possible for someone who had spent their formative years in a third of a gravity field. These are not minor uncertainties. They are the central unknowns of human Mars settlement, and they cannot be resolved by any amount of modeling or simulation. They can only be resolved by experiment, by placing human beings in partial gravity environments and measuring what happens to them over timescales of months and years. And here is the critical point. That experiment cannot be conducted on Mars, because conducting it on Mars requires first getting people to Mars, which requires solving the transit problem, which requires knowing enough about partial gravity to design appropriate countermeasures for the journey and the surface stay. The experiment needs to be conducted before the mission, not during it. The only way to conduct that experiment before sending people to Mars is to provide partial gravity somewhere closer, somewhere accessible, somewhere where a crew experiencing unexpected physiological complications can be brought home in days rather than years, somewhere in orbit. A rotating station in low Earth orbit, capable of varying its rotation rate to provide different gravity levels at the rim, is the instrument with which we answer these questions. It is a laboratory for partial gravity in the same way that the ISS is a laboratory for zero gravity, but unlike the ISS, it can be configured to study the full range of partial gravity environments that human expansion into the solar system will require us to understand. Run the rim at a rotation rate that produces 38% of Earth's gravity Martian surface conditions and study a crew for 12 months. Measure their bone density, their muscle mass, their cardiovascular parameters, their immune function, their sleep quality, their cognitive performance. Compare them to a control group living at full Earth gravity in the inner portions of the ring. Adjust the rotation rate to lunar gravity 1/6 of Earth's and run the same study with a different crew. After 5 years of such experiments, we will know more about the physiology of partial gravity than we have learned in 6 decades of spaceflight. We will know whether Martian gravity is adequate for long-term human habitation, or whether settlers will require supplemental gravity through centrifuge exposure. We will know whether children can grow up on Mars without lasting physiological consequences, or whether Mars will always require careful medical management of its population. We will know whether the transit to Mars should aim for Martian gravity, Earth gravity, or something in between, and whether different crew roles, medical officers, pilots, surface operations specialists might benefit from different gravity protocols during transit. These are answerable questions. They are not being answered because the instrument required to answer them does not exist. Building that instrument, the rotating station, is not preparation for going to Mars. It is a prerequisite for going to Mars responsibly. For going to Mars in a way that does not treat human crew members as acceptable casualties of our uncertainty about the physiological consequences of what we are asking them to endure. There is a version of the Mars mission that does not include rotation. That sends crews in conventional spacecraft, with exercise countermeasures and pharmacological support, and the best nutritional protocols currently available. That accepts the physiological risk of the transit and plans for an extended recovery period on the Martian surface before full mission operations begin. That version is not impossible. It may even be attempted in the spirit of the Apollo program, in the spirit of accepting significant risk in order to achieve something that would otherwise be delayed for years or decades. There are arguments for that approach that deserve to be taken seriously rather than dismissed. But there is another version, one where the first crews to reach Mars arrive, having spent 7 months in steady gravity, their bones intact, their muscles loaded, their cardiovascular systems maintaining the architecture they will need for the work ahead. One where the uncertainty about Martian gravity has been substantially reduced before the mission launches, because a decade of rotating station research has provided data that no other approach could generate. One where the transit vehicle is not a survivable ordeal, but a habitable journey. That version requires the rotating station to exist first. It requires us to make the decision that von Braun thought was obvious in 1952, and that we have been deferring ever since. The physics has not changed. The human body has not changed. What has changed is the urgency, because Mars is no longer a symbol or a speculation. It is a destination with a timeline, a destination that people alive today may reach within their lifetimes. And the question of how they will arrive, in what condition, with what capabilities, with what margin between success and catastrophe, is being shaped right now by decisions being made in engineering offices and funding committees and mission planning sessions around the world. The rotating station is not a footnote to those decisions. It is the foundation of them. Whether we recognize it or not, there is a phrase that surfaces repeatedly in the engineering literature on artificial gravity, a phrase that has the quality of something obvious that took decades to state clearly. Gravity is not a feature, it is infrastructure. When you design a building, you do not consider whether to include a floor. The floor is not optional. It is the precondition for everything else the building contains. You do not justify its presence by calculating the productivity benefits of having occupants stand upright rather than float. You include it because the building cannot function without it, and because the people inside it cannot function without it, and because the cost of omitting it is not a savings, but a different kind of expense, one paid not in construction budgets, but in the physical capacity of every human being who ever tries to live and work in the structure. The rotating station is the floor, not of a single building, but of every serious human presence in space that extends beyond a few months in duration. Everything built above it, the Mars missions, the asteroid operations, the cycler fleets, the eventual deeper ventures into the outer solar system, rests on whether we have solved the gravity problem before we need to rely on the people performing those missions to be physically capable of performing them. Von Braun knew this. He put the floor in the plan at step 2 before the moon. We skipped it. Now, we are designing buildings without floors and wondering why the occupants keep getting hurt. The answer has been the same for 70 years. And the moment we decide to act on it, the moment we commit to building the first rotating habitat in orbit, we will finally be completing the step that should have come before everything else. Not the end of something, the beginning. The beginning of the part where humans do not merely visit space, but live in it. Picture an asteroid, not the dramatic version, not the mountain of rock hurtling toward Earth that appears in disaster films, trailing fire and portending extinction. The mundane version, a body perhaps a kilometer across, irregular in shape, tumbling slowly in the darkness of the inner asteroid belt, somewhere between the orbits of Mars and Jupiter, dark, cold, unremarkable to any instrument that is not specifically looking for it. It is made of metal, not uniformly, not purely, but substantially iron and nickel in concentrations that would make any terrestrial mining operation profitable beyond calculation. Platinum group metals in quantities that exceed the total amount ever extracted from Earth's crust in all of human history. Water ice locked in shadowed craters, available for electrolysis into hydrogen and oxygen rocket propellant, manufactured in space, eliminating the most expensive and most limiting factor in every mission that currently has to carry its fuel all the way up from the bottom of Earth's gravity well. There are millions of objects like this, not thousands, millions, scattered across the belt, concentrated in certain orbital families, accessible from Earth orbit with the right vehicle and the right trajectory. The total material wealth contained in the asteroid belt has been estimated cautiously, conservatively, at quantities that make every economy in human history look like rounding error. We are not going there yet, but we are going. And when we do, the question of how the people who go there will live is not a secondary consideration to be addressed after the mining technology is developed. It is the primary constraint that determines whether any of it is possible at all. A mining outpost on a small asteroid does not need a mile-wide Stanford torus. It does not need 20,000 residents in an agricultural sector and a school system. It needs something rugged, capable of keeping a crew of perhaps 20 to 50 people healthy through rotations of a year or more, serviceable with the tools and materials that can be brought from Earth or fabricated on site, and expandable as the operation grows. It needs, in other words, something very close to a von Braun wheel, small, self-contained. designed not for permanence in the sense of monumental architecture, but for permanence in the sense of sustained function, the kind of permanence that a frontier trading post has, or a deep-sea research station, or a Antarctic overwinter camp. Enough to keep people alive and productive and reasonably healthy through the long, dark, isolated stretches that any serious resource extraction operation will involve. The asteroid itself provides something that no orbital station can easily replicate: shielding. Rock is an extraordinary radiation barrier. A meter of asteroid regolith, the loose, fragmented surface material that covers most small bodies, attenuates cosmic ray exposure to levels comparable to those at Earth's surface. 2 meters reduces it further. The radiation environment of deep space, which represents one of the most serious health risks for long-duration spaceflight beyond the protection of Earth's magnetosphere, becomes manageable when you can pile several meters of rock over your habitat. And on a small asteroid, with surface gravity so faint that a person could throw a baseball into escape velocity with a moderate effort, piling rock requires almost no structural engineering. The loads are negligible. A modest dome of inflatable polymer, covered in a few meters of regolith, shoveled over it by a small robotic system, provides radiation shielding that would require massive and expensive dedicated structures in free space. Imagine the sequence. A crew arrives at their target asteroid after a transit of perhaps 2 to 3 years from Earth. A transit conducted, in this future, aboard a rotating transfer vehicle that has kept their bodies functional throughout the journey. They do not arrive as patients, they arrive as workers. The transfer vehicle's rotating habitat ring is detached from the drive section and lowered carefully into a natural crater on the asteroid's surface. Not dropped in microgravity, even a gentle contact with the surface requires controlled precision, but settled on a handful of narrow pylons anchored into the regolith in a shallow bowl that the robotic advance team has prepared over the preceding months. The ring's rotation is maintained by electric motors drawing power from solar arrays deployed at the crater rim. A thin membrane dome is inflated over the ring, and regolith begins to accumulate on its outer surface hours of robotic work that gradually buries the entire assembly under 2 meters of radiation-blocking rock. Inside, the crew's home is turning, the floor is down, water falls when you pour it, sleep comes in a bed rather than a restraint system. The isolation is profound. Communications with Earth are delayed by minutes in each direction, rendering real-time conversation impossible and reinforcing the psychological reality of how far from home they have traveled. But the environment within the buried spinning ring is not hostile. It is constrained and Spartan and demanding in the ways that any frontier environment is demanding, but it is inhabitable in the full sense of that word, not merely survivable, inhabitable. The rest of the transfer vehicle is not wasted. The structural members become trusses for surface installations. The propellant tanks, emptied of fuel, become pressurized storage volumes or water reservoirs. The engine housings become machine bays, their interiors repurposed for the metal processing equipment that will eventually turn asteroid ore into useful material. The interplanetary vehicle that carried them across the solar system becomes the skeleton of the settlement they are building. Very little is discarded, everything is reconsidered. Outside the crater, the work begins. Surface operations in near-zero gravity require anchoring systems, lines and clips, and magnetic boots for the metallic portions of the asteroid, and a deliberate choreography of movement that takes time to master, but becomes, over weeks of practice, almost intuitive. Ore samples are collected and analyzed. Promising veins are identified. Extraction equipment, brought from Earth in pieces and assembled on site, begins its work. But the crew does not live on the surface. After a shift in near weightlessness, they return to the buried ring. They descend into the crater, cycle through the airlock, and step into a space where gravity is present and orientation is unambiguous. They eat meals at a table. They sleep in beds. They exercise not as medical countermeasure, but as recreation, because, in a partial gravity environment, the physiological maintenance that microgravity demands through mandatory exercise is largely accomplished by simply moving through the day. This is the functional division that the rotating habitat makes possible. Zero gravity for work for the delicate three-dimensional operations that microgravity actually facilitates, for the material handling and sample processing and equipment maintenance that benefit from the ability to move freely in all directions. Partial gravity for life, for rest, for meals, for the social and psychological activities that sustain human beings through long periods of isolation and physical demand. The wheel is not the whole of the outpost, it is the heart of it, the place where the crew's humanity is maintained while their professional focus turns outward to the cold and ancient rocks surrounding them. Now scale this picture outward, not in a single leap to an imagined future, but step by step, the way that frontier settlement has always actually proceeded. The first asteroid outpost is a proof of concept, a demonstration that human beings can live and work productively in the deep belt, that the physiological management is achievable, that the resource extraction technology functions in practice and not just in simulation. It returns its investment in scientific knowledge, in material samples, eventually in processed metal and water that can be used in space rather than launched from Earth. And it builds the institutional confidence and the engineering knowledge required for the second outpost. The second outpost is larger, more capable, perhaps 2 rotating rings, counter-rotated around the same axis for dynamic stability, providing more habitable volume and the redundancy that any serious long-term installation requires. The crew is larger. The operation is more sophisticated. The supply chain from Earth is more developed. The third outpost draws on lessons from the first 2. The fourth is designed by people who grew up knowing that asteroid mining is a real industry rather than a theoretical possibility. By the time there are 50 outposts in the belt, each one anchored around some variant of a rotating habitat, the cumulative population of the asteroid mining industry numbers in the thousands. Not thousands living in a single grand structure, thousands distributed across dozens of sites, in habitats ranging from modest rings 50 meters across to more elaborate multi-ring complexes serving as regional supply hubs and processing centers. None of these are cities. None of them are the vast orbital habitats that populate the more ambitious visions of space settlement. They are frontier towns, mining camps, trading posts, the kind of human settlement that has always preceded the cities, that has always been more numerous than the cities, and that has always been more important to the actual functioning of civilization than the cities receive credit for. Let us follow the logic in a different direction, away from the asteroid belt, back toward the inner solar system, back toward the space around Earth and Mars, where the traffic of an interplanetary civilization will eventually be densest. A mature human presence in the solar system is not a collection of isolated outposts connected by occasional supply missions. It is a network. It has traffic ships moving between destinations on regular schedules, carrying cargo and crew and information. It has infrastructure stations that serve as waypoints, refueling depots, transfer hubs, medical facilities, communication relays. It has an economy, with production occurring at multiple locations and distribution flowing between them. Every network requires nodes, and the nodes of an interplanetary network, the places where ships arrive and depart, where cargo is transferred and crews are exchanged, where the logistical threads of a solar system economy converge and diverge, are orbital stations. Not 1, not 10, eventually hundreds, eventually, if the most optimistic projections prove correct, thousands. What do those stations look like? Not all of them will be rotating. The smallest, the simplest, the most specialized automated cargo depots, communications relay platforms, navigation beacons will have no crew and require no habitation. But any station that houses human beings for periods longer than a few weeks, any hub where crews transfer between vehicles or wait for departure windows or receive medical care, any node where the human elements of the network are maintained and managed, these require habitation. And habitation, as we have now established through 60 years of increasingly expensive evidence, requires gravity. The rotating station as a port is a concept that deserves more attention than it typically receives in discussions of space infrastructure. Consider what a port actually does. It is not simply a place where ships stop. It is an interface between two different transportation modes, between the ship and the shore, between the mobility of the ocean and the stability of the land. It provides facilities that ships cannot efficiently carry for themselves: bulk storage for cargo, maintenance capacity for vessels too large or complex to be serviced underway, habitation for crews who need rest between voyages, commercial and administrative functions that require a fixed location. A rotating orbital station can serve exactly this function. Its hub, the central non-rotating section, is the port face, the docking interface where ships arrive and depart, where cargo is loaded and offloaded, where the transfer of crew and material between vehicles is managed in the microgravity environment that makes these operations most practical. Its rim, the rotating section, is the shore, the place where people live between voyages, where maintenance workers sleep and eat between shifts on the hull of a ship, where the human requirements of a working port are met in an environment that does not require them to fight their own physiology at every moment. This hybrid architecture, microgravity at the hub, partial or full gravity at the rim, is not a compromise between incompatible requirements. It is an integration of complementary ones. The zero-gravity environment of the hub is genuinely useful for certain operations. The handling of large, delicate cargo that would be difficult to manage under gravity, the precise maneuvering of spacecraft that must dock without introducing uncontrolled forces, the fabrication of structures whose geometry benefits from the absence of gravitational distortion during assembly. The gravity environment of the rim is genuinely necessary for the long-term health and productivity of the people who operate the port. The two environments coexist in the same structure, separated by the distance between the hub and the rim, a distance that can be traversed by elevator along the spoke, taking perhaps a minute or two of travel. Crew members move between them as their work requires. A shift at 0G, working on the hull of a docked vessel, then down the spoke to a meal at a table that holds the plate in place while they eat. This is, in miniature, the pattern of every successful port in human history. The ship and the shore, the mobility and the stability, the operational environment and the habitable one, separated by enough distance to be distinct and close enough to be practical. Now consider the numbers. Not the numbers of science fiction, not the population projections of optimistic futurists, but the conservative arithmetic of what a functioning interplanetary economy eventually requires. If Mars achieves a permanent human population of 50,000 people, a number that sounds large until you compare it to any mid-sized city on Earth, and if those people require regular resupply from Earth, or asteroid mining operations until local production is self-sustaining, then the traffic between Earth and Mars will involve dozens of ships per launch window, cycling between the two planets on schedules determined by orbital mechanics. Those ships need somewhere to load and offload. They need maintenance. Their crews need rest and recovery between transits. The Aldrin cyclers that carry passengers need terminal facilities at both ends of their routes, where the transfer vehicles that ferry crew to and from the cycler can operate efficiently. Each of these requirements implies a station, not a research platform or a demonstration project, but an operational hub with the infrastructure of a working port: storage, maintenance, habitation, power, communications, medical facilities, and habitation, as we keep returning to, means gravity. How many such stations? The arithmetic is not precise, but the order of magnitude is instructive. Even a conservative model of inner solar system traffic, Earth-Mars shipping, asteroid belt supply chains, lunar operations, the early stages of outer planet exploration, implies dozens of major orbital nodes within a century of sustained development. More if the economy grows faster than the conservative projection, fewer if it grows more slowly. Dozens of major nodes, each one a rotating habitat, each one a wheel, in the broad sense mass distributed at radius, spinning to provide the gravity that its human occupants require, plus the smaller nodes, the regional depots, the transfer points, the research outposts, the private habitats of communities that have decided to build their own piece of the network, plus the cycler ships, plus the transit vehicles on long missions, plus the asteroid outposts. Add them together. Not the grand total of some specific projection, but the accumulation of a civilization extending itself across the solar system through the only means by which civilizations have ever extended themselves. The proliferation of inhabited places, each one connected to the others by the flows of people and material and information that give a civilization its coherence. The number of rotating habitats in a mature solar system civilization is not 10, it is not 100, it is thousands, tens of thousands eventually, most of them small, most of them modest, most of them doing the unglamorous work of keeping people alive and productive in environments that would otherwise be uninhabitable, most of them, in their fundamental geometry, descendants of a design that was sketched out by a German-American rocket engineer in 1952, before the space age began, in a proposal that was read by millions and implemented by no one. There is a pattern in the history of technology that is so consistent, it almost qualifies as a law. The structures that define a civilization are not its largest ones. They are its most replicable ones. The Roman Empire was not defined by the Colosseum. It was defined by the standard design military fort, the castra, reproduced across 40,000 kilometers of frontier, with such consistent geometry that archaeologists can identify the remains of one in Britain by same spatial logic they use to identify one in Syria. The design was not beautiful. It was not ambitious. It was functional, reproducible, and good enough for the purpose. And it was produced by the thousands. Medieval civilization is remembered through its cathedrals. But the cathedrals were few, and the towns were many, and the towns were built around the same basic pattern of market square and parish church and defensive wall, repeated across 10,000 settlements with local variation but consistent logic. The cathedral was the monument, the town was the civilization. The Industrial Revolution produced mills and factories that we now preserve as heritage sites, vast and imposing structures whose architectural ambition expressed the optimism of the era. But the revolution ran on the tens of thousands of smaller workshops and foundries and machine shops that built the components and processed the materials that the large factories required. The supply chain, not the flagship plant. Space civilization will follow the same pattern. The Stanford Torus will be a monument, a genuine feat of engineering that will house tens of thousands of people and generate justified wonder from anyone who sees it rotating in the sunlight. The O'Neill cylinder will be a city-state, an enclosed world of millions, a structure whose existence changes the meaning of the word settlement. These things will be built, eventually. They will be magnificent, but they will not be the foundation of interplanetary civilization. They will be its cathedrals. The foundation will be the wheels, small enough to be built with the technology of any given decade, rather than requiring the accumulated industrial capacity of a century, large enough to house dozens or hundreds of people in conditions that sustain long-term human health and productivity, modular enough to be expanded as needs grow, combined with other rings when larger configurations are required, repurposed from transit vehicle to surface outpost to orbital hub as the mission changes, numerous enough to form the distributed network that any functioning civilization requires. The ports and depots and trading posts and research stations and private communities that connect the larger nodes and fill in the spaces between them. Two wheels linked at their hubs become a larger complex, with counter-rotating rings for dynamic stability. 4, arranged around a common docking spine, form a small orbital village. 10, sharing infrastructure and connected by pressurized passages, it becomes something that begins to have the character of a community rather than an outpost. A place with enough population to develop internal social structure, to support specialized roles, to accumulate the institutional knowledge that makes a settlement self-sustaining rather than dependent. This is how civilizations grow, not through single grand gestures, but through the accumulation of smaller ones, each justified by the conditions of its moment, each creating the conditions for what follows. The log cabin precedes the farmhouse. The farmhouse precedes the town precedes the city, and at every stage, the smaller, earlier structure is more numerous than what came after it. In the solar system, the wheel is the log cabin, not the final form, but the first viable one, not the destination, but the path. And paths, by their nature, are walked one step at a time. There is something worth sitting with before we move to the final part of this journey. Von Braun's wheel was drawn in 1952. The people who would eventually walk on the moon were, in that year, children. The first artificial satellite was 5 years in the future. The concept of a space station was not science. It was science fiction. In the eyes of most people who encountered it, a fantasy as distant from practical reality as the flying cars and rocket packs of the pulp magazines. And yet the drawing was correct. The physics was right. The engineering was serious. The sequence made sense. Step 1, then step 2, then step 3. Build the foundation before the house. We built the house without the foundation. We went to the moon without the station, and then we went to the station without the rotation, and now we are discussing Mars without having resolved the rotation question that should have been answered decades ago. We have been building, impressively and at enormous cost, on ground that was never fully prepared. The foundation is still available. It was never unavailable. It has been waiting with the patience of a geometric fact for us to return to step 2 and complete what the roadmap always required. We are closer to that moment now than we have ever been. The launch economics are better. The engineering knowledge is deeper. The medical case is stronger. The missions that a rotating station enables are no longer hypothetical, they are being planned, with timelines measured in years rather than decades, by organizations that have the resources and the will to attempt them. What happens when we finally build it, when the first rotating habitat spins up in orbit and a crew steps off a spoke into the rim and feels the floor press against their feet, is not the end of a long delay. It is the beginning of everything that the delay postponed. Consider something so ordinary that you have never once thought about it. You are holding a glass of water. You tilt it. The water falls. It falls in the direction you expected, at the speed you expected, into the container you positioned to receive it, without requiring you to think about fluid dynamics or pressure differentials or the behavior of liquids in enclosed systems. The water falls because gravity pulls it downward, and downward is unambiguous, and you have known since before. You could speak which direction downward is. Now remove that certainty. In the microgravity environment of every crewed spacecraft ever built, water does not fall. It floats. Released from a container, it forms a sphere surface tension holding it together in a trembling globe that drifts slowly in whatever direction it was moving when you released it. To drink, you squeeze fluid from a sealed pouch directly into your mouth, because a cup is useless when the liquid will not stay in it. To wash your hands, you use a minimal amount of water and work quickly before the droplets escape and begin migrating toward air intake vents, where they will be drawn in and potentially cause problems for equipment that was not designed to handle water ingestion. Every liquid interaction in microgravity is a problem to be managed, not a crisis, not an emergency, a problem. A small, persistent, energy-consuming problem that recurs every time you need to drink, every time you need to cook, every time you need to clean, every time any process that relies on the simple, ancien, taken for granted fact of water moving downward is attempted in an environment where downward does not exist. Multiply that problem across every system in a spacecraft or space station, every fluid system, every thermal management loop, every biological process that evolved in a gravity field and now must function without one. Add it to the exercise requirement, the sleep medication, the toilet engineering, the handhold choreography of movement through a space where drifting in the wrong direction is a constant possibility. This is what it costs to live in microgravity, not dramatically, not catastrophically, quietly, persistently, across every hour of every day, in the form of attention and energy and time diverted from the actual purpose of being in space toward the management of an environment that was never designed for human habitation. A rotating station does not solve every problem of space habitation. Let that be clear. Radiation shielding remains a challenge regardless of gravity. Resupply from Earth remains expensive, regardless of how comfortable the destination is. Psychological isolation, the specific cumulative weight of being far from home, separated from the people and places and sensory experiences that define ordinary human life, is not meaningfully reduced by the presence of a floor beneath your feet. But the floor matters. More than any single engineering feature, more than any individual countermeasure or technological innovation, the presence of a consistent gravitational direction transforms the character of daily life in space from managed survival to something approaching inhabited normality. Water falls when you pour it. That alone, that single, trivial, profound fact, changes the nature of cooking, of cleaning, of hydration, of every biological process that requires fluid movement in a predictable direction. Plants orient themselves toward light along an axis that gravity defines, which means they grow in recognizable patterns rather than the arbitrary spirals that space station botanists must constantly manage and redirect. Air circulates in thermal layers, warm air rising, cool air sinking rather than dispersing uniformly in all directions, which means that ventilation systems can be simpler and the air quality in different parts of the station naturally varies in ways that human biology evolved to navigate. Sleep comes without restraints. This is not a small thing. The psychological cost of sleeping strapped to a wall, of surrendering the unconscious freedom of movement that every sleeping human body expects, and of waking to find yourself in exactly the position you were in when you closed your eyes, because there is no gravity to roll you over, accumulates across months of a long mission in ways that are difficult to quantify, but consistently reported by crew members as one of the most persistently disorienting aspects of orbital life. In a rotating station, you sleep in a bed. You wake, having moved, as bodies do during sleep, in the directions that your body chose. The night is not a managed physiological process. It is rest. Tools stay where you put them. This is another statement so simple that its implications require a moment of attention. In microgravity, every object that is not actively held or tethered is a potential problem. A wrench set down during a repair drifts away. A screw released for a moment to reposition a hand floats toward the nearest air intake. The small, constant, unconscious act of setting something down and trusting that it will be in the same place when you reach for it. An act so fundamental to human tool use that we never consciously perform. It does not exist in a weightless, accursed environment. Every tool must be tethered. Every component must be tracked. Every hand that releases an object must make a deliberate decision about where that object will be when the hand needs it again. The cognitive load of this is real. Not paralyzing crews adapt, develop habits, learn the microgravity choreography of their workspace, but persistent. A portion of attention that would, in a gravity environment, be available for the actual task at hand is permanently allocated to the spatial tracking of equipment and the prevention of the slow, entropic drift of objects away from where they need to be. In a rotating station, you put the wrench down. It stays. You pick it up. The transaction is complete in exactly the time it takes to perform it, with no cognitive overhead allocated to gravity management. The maintenance task that takes 3 hours in microgravity, not because the repair itself is complex, but because the environment requires constant management of tools and positioning, and the prevention of component drift, takes 2 hours in a gravity environment, perhaps less, if the task is one where the ability to brace against the floor with both feet, rather than needing one hand constantly for stability, allows more efficient use of the available force. This is not a marginal efficiency gain. Across the full scope of maintenance, repair, assembly, and manufacturing operations that a long-duration space presence requires, the productivity difference between a microgravity workspace and a partial gravity workspace is substantial. Not because microgravity workers are less skilled or less diligent, but because the environment imposes costs that gravity simply does not. Consider agriculture. Any human presence in space that extends beyond the range of practical resupply from Earth, any outpost in the asteroid belt, any settlement on Mars, any crewed station intended to be partially self-sustaining rather than wholly dependent on supply chains from the home planet, must eventually grow food, not as a supplement to shipped supplies, but as a primary caloric source, because the alternative is a supply chain of such scale and cost that it dominates the economics of the entire enterprise and places any disruption in that chain in the category of existential risk. Growing food in microgravity is possible. It has been demonstrated, repeatedly, in small-scale experiments aboard the ISS, lettuce and radishes, and a handful of other fast-growing crops, cultivated in specially designed growth chambers with precise lighting and carefully managed nutrient delivery systems. The plants grow. They are edible. The crew members who tend them report psychological benefits from the presence of living, green things in an otherwise entirely mechanical environment. But growing food at scale in microgravity is complicated in ways that gravity quietly resolves. Root systems in microgravity do not orient downward by gravitational tropism, the automatic, reliable tendency of roots to grow toward gravity and stems to grow away from it that makes terrestrial agriculture largely self-managing at the level of individual plant geometry. In microgravity, roots grow in whatever direction local chemical gradients and moisture distribution suggest, which requires growth media to be carefully engineered to provide the directional cues that gravity normally provides for free. Water delivery to plant roots in microgravity requires active management pumping rather than draining, careful pressure control, and prevention of the bubble formation in root zones that occurs when water cannot drain freely in a predictable direction. Nutrient solutions that would naturally stratify and circulate in a gravity field must be mechanically stirred. Seeds that would germinate with predictable orientation must be planted in specifically designed substrates. None of these are insurmountable. All of them are additional engineering requirements, additional systems that must be designed, built, tested, maintained, and repaired on top of the already formidable challenge of growing food in the radiation and vacuum environment of space. In a rotating station, plant roots grow downward, water drains, nutrients stratify, seedlings orient themselves correctly without intervention. The agricultural engineering problem is reduced, not to the trivial level of terrestrial farming, but to something considerably closer to it than the microgravity version, something that can be approached with techniques and intuitions refined over 10,000 years of human food production, rather than requiring the reinvention of every principle of agronomy. The difference, in practical terms, is the difference between a growth system that requires active management at every step and one that can be partially self-managing. In a large agricultural module on a rotating station, you can plant a row of crops and trust that gravity will do a portion of the work of keeping them oriented, watered, and drained. The system's engineering burden decreases, the failure modes narrow. The expertise required to manage the system becomes less exotic. Food production in space is never simple, but it is simpler in gravity than without it, by enough that the difference matters enormously when the alternative is starvation. There is a category of space activity that rarely appears in public discussions of rotating habitats, perhaps because it belongs to a future that feels more distant than Mars missions or asteroid mining. But it is worth examining because it represents the ultimate expression of what artificial gravity makes possible in space. Manufacturing. Human industrial production evolved in a gravity field. The tools, the techniques, the intuitions, the accumulated institutional knowledge of how to shape material into useful objects, all of it was developed by people standing on floors, using their weight for leverage, relying on gravity to do a portion of the work of material handling, sedimentation, casting, forming, and assembly. Some manufacturing processes actually benefit from microgravity. Crystal growth in the absence of convective currents produces more perfect structures than is possible on Earth. Fiber drawing, foam formation, and certain types of alloy production are genuinely improved by weightlessness. There is real and legitimate scientific and industrial interest in microgravity manufacturing that should not be dismissed. But the workers who operate the manufacturing equipment are not improved by weightlessness. They are hampered by it in all the ways we have already examined: the tool management, the positional control, the cognitive overhead of working in an environment that their bodies were not designed for. And the manufacturing processes that benefit from microgravity can be conducted in dedicated zero-gravity modules at the hub of a rotating station, while the workers who tend those processes live and eat and sleep in the gravity environment of the rim. As orbital industry develops, and it will develop, because the material resources available in space are essentially unlimited compared to the constrained reserves of a single planet. The productivity advantage of a gravity-enabled workforce will compound, not in every process, and not by the same margin in every application, but consistently enough that the rotating station becomes not just a health management solution, but an economic one. A workforce that spends 2.5 hours per day on mandatory exercise has less time for productive work than one that does not. A workforce that sleeps poorly has lower cognitive performance than one that sleeps in beds. A workforce whose tools drift away requires more time to complete tasks than one whose tools stay where they are put. These are not dramatic differences in any individual instance. Accumulated across a workforce of thousands, across years of operation, they represent a substantial difference in the output of a space-based industrial enterprise. Gravity is a productivity multiplier, not because it makes people work harder, but because it removes the constant ambient friction of an environment that fights human ergonomics at every interaction. And then there is something harder to quantify but no less real, the psychological dimension. Human beings are not purely rational processing systems. We are biological entities with deep evolutionary histories, with needs that extend beyond caloric intake and physiological maintenance into the territory of comfort, meaning, continuity, and the subtle sensory textures of a world that feels like ours. The ISS is a marvel of engineering. It is also, by the consistent report of everyone who has lived aboard it, a profoundly strange place to be a human being. Not merely isolated, isolation is manageable, as the long history of polar exploration and submarine service and remote research stations demonstrates. Strange in a more fundamental way, oriented wrong, moving wrong, feeling wrong in the body in ways that are not dramatic but are constant, like a sound at a frequency just at the edge of perception that you cannot quite identify but cannot quite ignore. Astronauts report adapting to microgravity. They report becoming comfortable with it, developing competence in it, even finding a kind of freedom in it. They also report, with remarkable consistency, that the moment of return to Earth, the first sensation of weight pressing them into a chair as the capsule descends through the atmosphere is accompanied by something that is not quite relief, but is close enough to it that the distinction barely matters. The body recognizes its native environment, and when it is returned to that environment after months of absence, something that was held slightly wrong for the entire duration of the mission relaxes. A rotating station does not replicate Earth. It cannot. The view through the windows is still the curve of a planet and the black of space. The air still recycles through the same filters. The social world is still a small, closed group of people who must find ways to coexist in confined circumstances across months or years of shared experience. The distance from home is still absolute, but the floor is down. The water falls. The body's most fundamental spatial orientation, the one calibrated over 4 billion years of evolution under the unbroken pull of planetary gravity, is correct. And that correctness, that single restored certainty, changes the character of everything around it in ways that are difficult to articulate, but easy to recognize in the testimony of the people who have lived without it. A crew member who sleeps in a bed, wakes without restraints, eats from a plate, and moves through a corridor with gravity orienting. Every step is living in a place that makes demands on human adaptability, but does not assault human biology at its most basic level. They are challenged by the mission, by the isolation, by the complexity of the work and the weight of the responsibility. They are not also being challenged by the simple act of existing in a body that was built for a different kind of world. That is not a luxury. It is the difference between endurance and habitation. There is a word that comes up repeatedly in discussions of what space settlement means, beyond the engineering and the economics and the mission profiles. Home. Not in the sentimental sense, not the nostalgia for a specific place or the attachment to childhood landscapes. In the functional sense, a place where the basic requirements of human existence are met without conscious effort, where the physics cooperates rather than resists, where the body can rest and the mind can direct its attention outward, toward the work and the relationships and the meaning that justify the enormous investment of being somewhere as difficult as space. No station in the history of human spaceflight has been a home in this sense. They have been extraordinary achievements. They have been places where extraordinary people have done extraordinary things under extraordinary conditions. They have been laboratories and research platforms and political symbols and engineering demonstrations. They have not been homes. The rotating station is the precondition for home. Not sufficient on its own, a rotating station is still an enclosed, artificial environment with all the constraints that entails but necessary. The floor is the beginning of home. The water that falls is the beginning of home. The bed without restraints is the beginning of home. Everything that has ever been called a home, in every culture and every era of human history, shared one thing. Weight pressed your feet to the floor. You knew which way was down. Your body existed in the environment it was built for. The rotating station gives that back. Not Earth, not the specific gravity of the specific planet where humanity spent its entire evolutionary history, but gravity, manufactured, reliable, ours. And from that foundation, from the floor of the first spinning ring in orbit, everything that a civilization in space might eventually become, becomes imaginable in a way it has not quite been before. Not a population enduring the conditions of space, a population living in them, not astronauts on missions, people with lives, not the destination of an expedition, the beginning of a world. The von Braun wheel was drawn before any of this was possible, before the rockets, before the materials science, before the 60 years of physiological data that now make the argument for artificial gravity so clear that it barely requires argument. It was drawn by someone who understood that the human body is not optional equipment in the project of space settlement, that you cannot design for space and design against biology at the same time and expect the result to be a place where human beings can actually thrive. He put the wheel in step 2, before the moon, before Mars, before any of the destinations that captured the imagination of the century that followed. He understood something that took us 70 years of data to confirm. You cannot build a civilization in a place where the floor is missing. And now, finally, we have everything we need to install one. We began with a drawing, not a painting, not a rendering designed for public consumption or political persuasion. A drawing the kind made by engineers who are thinking with their hands, who put lines on paper, not to impress, but to test whether an idea holds together when forced into specific geometry and specific numbers. A wheel, 75 meters across, turning slowly above the curve of the Earth, with spokes connecting a central hub to an outer ring where the floor was always down and the water always fell. The year was 1952. The man who made it had already spent decades thinking about what it would take to send human beings beyond the atmosphere and keep them alive when they got there. And his conclusion arrived at through physics rather than sentiment, through the logic of what the human body requires rather than the romance of what the human imagination desires, was that the first thing you needed, before the moon, before Mars, before any destination that lay beyond the thin shell of air surrounding this planet, was a floor. Not a metaphorical floor, a literal one. A surface that gravity pressed you toward, that oriented your body in the direction it was built to face, that allowed the 10,000 biological processes evolved under 4 billion years of planetary gravity to function the way they were designed to function. That floor was never built, and the cost of that absence has been paid, quietly and persistently, across 6 decades of human spaceflight, in the bone density of every astronaut who returned from a long mission, in the mandatory exercise hours that consumed the time of every crew member who might otherwise have spent those hours on the work they went to space to do, in the sleep medication consumed at 10 times the rate of the general population by the most carefully selected and medically prepared human beings on the planet, in the missions that were not attempted and the durations that were not extended and the destinations that remained unreachable because the physiological price of reaching them was considered too high. The summary of what we know is not complicated. Zero gravity destroys the human body over timescales measured in months. The destruction is not immediate and not irreversible in the short term, but it is consistent, measurable, and cumulative in ways that become irreversible given sufficient time and insufficient countermeasure. The countermeasures we have developed are real, and they are impressive, and they are inadequate, not because of any failure of the scientists and engineers who developed them, but because they are managing a symptom rather than treating a cause. The cause is the absence of gravity. The treatment is gravity. The machine for providing gravity in space is a rotating structure. The rotating structure was designed in 1952, validated by physics that has not changed and never built. This is where we are, and this is where we begin, finally, to go somewhere different. The first rotating habitat in orbit will not look like the illustrations in the old Collier's magazine. It will be more modest. A ring perhaps 60 or 70 meters across, spinning slowly, housing a crew of dozens rather than 1,000, generating Martian gravity rather than Earth normal at the rim, because Martian gravity is what we most urgently need to understand, and because the lower rotation rate reduces the Coriolis effects that concern researchers studying crew habitability. It will not be beautiful in the way that the artists of the 1950s imagined. It will be functional in the way that all first-generation infrastructure is functional utilitarian, somewhat rough, clearly provisional, shaped by the constraints of what was possible to build rather than what was ideal to inhabit. The log cabin of the orbital frontier, exactly as von Braun imagined the wheel to be, not the final form, but the first viable one. But inside it, something will happen that has never happened before in the history of human spaceflight. A crew member will walk from the docking hub down a spoke into the rotating rim and feel the floor rise up to meet their feet and stand in space with their weight pressing downward in a direction that their body recognizes without being told. They will put a glass of water on a surface and release it. The glass will stay. The water, if they tilt it, will fall. They will sleep in a bed that night, a real bed, with no restraints, in an environment where their body can shift position during sleep, the way bodies have always shifted during sleep, since before the first human beings had words for sleep or for the gravity that made it possible. That moment, quiet, ordinary, and entirely unprecedented, will be the most significant event in the history of human space habitation since the first human being left the atmosphere. Not because of what it demonstrates technically, the physics was never in question, but because of what it means about the kind of future we are building. There is a concept in architecture called the difference between a place and a space. A space is a volume enclosed, pressurized, habitable in the minimal sense of keeping its occupants alive. A place is something more, a volume that has acquired the qualities of habitation, that has been shaped by and for the human presence within it, that reflects in its design the full range of what human beings need rather than merely the physiological minimum. Every crewed spacecraft ever built has been a space. The ISS is a space, an extraordinary one, a monument to engineering and international cooperation, but a space nonetheless, a volume where human beings can survive. The rotating station is the precondition for a place, not itself a place. Necessarily a first-generation rotating habitat is too small, too constrained, too provisional to fully earn that description, but the beginning of the trajectory toward one. The first structure in space that treats gravity not as a luxury to be dispensed with in the interest of simplicity, but as a prerequisite of habitation that must be provided at whatever engineering cost, because without it, you are not building a home, you are building a very expensive machine for keeping people alive in conditions they were not designed for. Every place that human beings have ever called home has had gravity. Not always the same gravity, not the same geology or climate or social structure or physical configuration, but always the pull of a planetary body. Always the floor pressing up against the foot. Always the water moving downward. Always the body oriented the way it was built to be oriented. The rotating station gives that back. For the first time, outside the gravity well of any planet, manufactured from first principles. Ours by design rather than by accident of birth on a particular world. Think about what follows from the first rotating habitat, if we have the patience and the commitment to follow the thread all the way through. The partial gravity research conducted aboard it resolves the uncertainty about Martian surface conditions. We learn, from controlled experiment rather than dangerous guesswork, whether 38% of Earth's gravity is sufficient for long-term human health. If it is, Mars settlement becomes physiologically straightforward, not easy, not without challenge, but straightforward in the sense that the fundamental biological question has been answered. If it is not sufficient, we learn that too, and we design the Martian settlements accordingly, with centrifuge facilities or rotating sections that supplement the planet's native gravity to whatever level the data suggests is necessary. Either answer is better than no answer, and right now we have no answer, because we have never built the instrument required to generate one. The first Mars transfer vehicle with a rotating section carries its crew across the interplanetary distance in steady partial gravity. They arrive physiologically intact. The mission profile that was designed around the assumption of capable, healthy crew members on arrival can be executed without the recovery period that every previous mission architecture quietly accepted as inevitable. The surface operations begin on schedule. The geology is sampled, the resources are assessed. The first human footprints on a second world are made by people whose legs could bear their weight. The Aldrin cyclers eventually carry passengers, not crew members on scientific missions passengers, people who have decided, for their own reasons, that they want to live somewhere other than the planet where they were born. The transit is 7 months. In a rotating cycler, those 7 months are spent in gravity. The journey is long and isolated and demanding, in the way that any long ocean voyage is long and isolated and demanding. But it is survivable without medical consequence. The passengers arrive on Mars, able to walk off the ship under their own power. The asteroid outposts are established, and the miners work their shifts in near weightlessness and return each evening to the buried rotating ring that is their home, and eat dinner at tables, and sleep in beds, and wake the next morning to the particular beauty of a sky, visible only through instruments but present nonetheless in the data streams that keep them connected to the civilization they represent here, at the edge of the explored solar system. And the wheels multiply. Slowly, at first each one built at significant cost, occupied by professional crews, justified by specific missions and specific economic calculations. Then faster, as the engineering matures and the costs fall and the demonstrated reliability of rotating habitats accumulates into the kind of track record that makes private investment possible. Then faster still, as the distinction between crewed station and commercial habitat begins to blur, as the population of permanent orbital residents grows from dozens to hundreds to thousands, as the solar system begins to acquire the character not of a frontier visited by expeditions, but of a domain inhabited by a civilization. Each of these habitats, in its fundamental geometry, a descendant of the drawing made in 1952, mass distributed at radius, spinning to provide what the void refuses to give, the floor always down. There is a kind of optimism that is easy and a kind that is difficult. The easy kind imagines a future of abundance and expansion and technological triumph, without reckoning honestly with the obstacles that lie between here and there, without acknowledging the genuine difficulty of what must be accomplished, the genuine uncertainty about whether it will be accomplished on any particular timeline, the genuine possibility that the path from where we are to where we want to be is longer and harder than the optimism would prefer to admit. The difficult kind looks at the obstacles clearly, counts them, understands them in their specificity rather than their generality, and then, having done that accounting honestly, concludes that the destination is still worth pursuing, not because the path is easy, but because the destination matters enough to justify a path that is not. The rotating station is a difficult optimism. It is not inevitable. It is not imminent. It requires decisions that have not yet been made, resources that have not yet been committed, and political will that has not yet been sustained across the administrations and budget cycles, and competing priorities that erode every long-term program. It requires us to treat a geometric fact about spinning rings and centrifugal acceleration as urgent infrastructure, rather than interesting theory. None of that is guaranteed. History offers plenty of examples of ideas that were correct, feasible, and never implemented, not because they failed, but because the conditions for their implementation never quite aligned, because the urgency that would have focused resources and attention never quite materialized. But history also offers something else. It offers the cumulative weight of evidence. And the evidence, after 70 years of human spaceflight and the physiological data of every long-duration mission ever flown, is no longer ambiguous. The body needs gravity. The missions need capable crews. The civilization we are beginning to build beyond Earth needs flaws. The argument has been won. What remains is the building. Von Braun put the wheel at step 2, not because he was romantic about spinning structures or attached to a particular engineering aesthetic, because he understood something that the subsequent 7 decades have confirmed at substantial cost, that you cannot build a presence in space that is worthy of the word civilization without first solving the most basic problem of human habitation in that environment. The most basic problem is not propulsion. We have propulsion. It is not life support. We have life support. It is not communication or navigation or power generation or any of the other technical challenges that dominate the engineering literature of spaceflight. It is gravity, the flaw, the thing so fundamental to every moment of human existence on this planet that we have no word for its absence except weightlessness, a word that sounds like freedom and feels, over months of experience, like a slow and quiet emergency. The wheel was never cancelled. It was postponed. And postponements, if they extend long enough without a specific moment of recommitment, can begin to feel permanent in a way that is distinct from cancellation. Not a decision against, but a decision deferred until the deferral becomes the decision. We are at the moment when that deferral ends, not because someone has declared it so, not because a government has committed the resources, not because the political and economic conditions have aligned in the specific way required to convert a correct idea into a built structure, but because the alternative, continuing to design for human presence in space, while declining to solve the most fundamental problem of human presence in space, has become untenable in the face of the missions we are now actually planning. You cannot send people to Mars in physiological freefall and call it a program. You cannot establish permanent human settlements beyond Earth without providing the conditions under which human beings can permanently inhabit them. You cannot build a civilization without flaws. Somewhere above you, right now, the International Space Station is passing overhead. It moves fast enough that it crosses the sky in a few minutes. A bright point of light that could be mistaken for a satellite or a high-altitude aircraft if you did not know what you were looking at. Inside it, 6 human beings are living in a space that has no flaw. They are extraordinary people doing extraordinary work in conditions that require them to be extraordinary simply to function. They are the inheritors of 60 years of accumulated knowledge about how to keep a human body alive in an environment that was never designed for human bodies. They exercise their mandatory hours. They sleep in their restraints. They take their medications. They do science that cannot be done anywhere else, and they do it with a competence and commitment that has no adequate counterpart in ordinary experience. They deserve a flaw, not as a reward, not as a comfort amenity justified by morale considerations or crew welfare metrics. As the infrastructure that every serious long-duration human presence in space has always required, and that we have, for 70 years, declined to provide. The next station does not have to repeat that absence. The next crewed vehicle bound for Mars does not have to subject its crew to 7 months of physiological deterioration. The next generation of humans who choose to make their lives beyond Earth does not have to choose between their health and their ambitions. The physics is ready. The engineering is ready. The medical case has been made, redundantly and irrefutably, by 60 years of data generated by the people we sent into space without the infrastructure they needed. What is required is the decision, the sustained, institutional, generational decision to treat the rotating habitat not as a future aspiration but as a present necessity, as step 2 in a roadmap that has been waiting with the patience of a correct idea for us to return to it. There is a final image worth holding. In the early years of a rotating station's operation, before the larger habitats, before the Mars missions, before the asteroid outposts and the cycler fleets and all the accumulated infrastructure of a civilization that has finally learned to live beyond the gravity well of its origin, a crew member will stand at a window in the rim of the station and look outward. Below, the Earth, moving slowly across the field of view as the station rotates, blue and white, and impossibly vivid against the black. Above, the stars, fixed, unblinking, present in their billions in a sky that has no atmosphere to scatter their light into daytime or soften their edges into the approachable constellations of a summer night. They are not points of possibility or symbols of aspiration. They are places, destinations, futures, and the crew member stands there, feeling the floor beneath their feet. Not the floor of a planet, the floor of a machine we built to replace the one we left behind. A floor that exists because someone understood, 70 years before it was constructed, that you cannot ask human beings to live in a place that has no down, that you cannot build a civilization without first building the infrastructure that makes civilization possible. The station turns, the Earth passes, the stars hold their positions, unchanged by our presence or our absence, indifferent to whether we reach them or remain behind. But the reaching, if it happens, the genuine, sustained, multi-generational expansion of human presence into the space between the stars will begin here, in the spin of a ring above a planet, in the quiet confirmation that the floor is down, in a drawing made before the space age by a man who understood that the first step into the cosmos was not a footprint on the moon or a flag on Mars, but something far more ordinary and far more profound. A place where water falls, where the body knows which way is down, where a human being, finally, in the darkness between worlds, can simply stand